Right now, at this very moment, something extraordinary is unfolding 125 million miles from Earth, and not a single human eye can witness it. Today, October 29th, 2025, at exactly 11:47 Universal Time, the interstellar object 3I Atlas reached its closest point to the Sun, hurtling through space at 68 kilometers per second, faster than any interstellar visitor we've ever tracked. This is what astronomers call perihelion, the moment when a comet's journey brings it nearest to our star, when sublimation explodes across its surface, when ice turns to gas in violent bursts, when the cosmic traveler reveals its true nature. But here's the problem: the maddening irony that has scientists around the world frustrated and fascinated in equal measure. 3I Atlas is completely invisible to us. The timing couldn't be more dramatic or more suspicious, depending on who you ask. Harvard physicist Michio Kaku called today Judgment Day, the moment when we would finally know whether this object speeding through our solar system is a natural comet or something built by intelligence. He told reporters just 3 days ago that the world will know if there are aliens in 3 days, that October 30th would determine if we're looking at rock and ice or alien technology. But the universe, or perhaps something else, had other plans. From October 21st, 8 days before perihelion, 3I Atlas vanished behind the Sun in what astronomers call solar conjunction, positioning itself on the exact opposite side of our star from Earth. Every telescope on our planet, from amateur backyard instruments to the most powerful observatories, became instantly useless. The object entered what scientists are now calling the dark period, a 40-day window from October 1st to November 9th, when 3I Atlas remains less than 30 degrees from the Sun, too close to observe safely or effectively. Think about what that means for a moment. The most important astronomical event of the year, perhaps of the decade, is happening right now in complete secrecy. As you read these words, 3I Atlas is being bombarded by approximately 33 gigawatts of solar radiation, roughly equivalent to the output of 33 nuclear power plants focused on a single object. The surface temperature is skyrocketing. Ice is sublimating at rates we can only estimate. If it's a natural comet, as most scientists insist, then massive amounts of gas and dust should be erupting from its nucleus, creating a brilliant coma and tail. The heating at perihelion, about 770 watts per square meter, could potentially tear the object apart if it's held together by weak gravitational forces, breaking it into smaller fragments that would evaporate even faster due to their increased surface area. But if it's something else, if Avi Loeb's controversial hypothesis holds even a grain of truth, then this moment represents the optimal time for an Oberth maneuver, a gravity-assisted speed boost that only a controlled spacecraft could execute. The frustration in the scientific community is palpable. Here we have an object that traveled for millions, possibly billions of years through interstellar space, an ancient wanderer from the thick disk of the Milky Way, and it chose to make its closest approach to our Sun at precisely the moment when we cannot watch. Some call it cosmic coincidence. Others whisper darker possibilities. The conspiracy theorists have latched onto a curious detail. A classified military meeting occurred on September 30th, just before 3I Atlas entered its invisible phase, and the U.S. government experienced a partial shutdown in October, during which data from Mars orbiters mysteriously remained unpublished. NASA added 3I Atlas to the International Asteroid Warning Network on October 24th, marking the first time an interstellar object has been included in planetary defense protocols. Their official reason? The unpredictability of comet jets. Their unofficial silence on other matters speaks volumes to those inclined to listen. But we're not completely blind. A handful of spacecraft scattered across the inner solar system have maintained visual contact with the comet, providing tantalizing glimpses of what's happening during this critical passage. The GOES-19 weather satellite, designed to monitor Earth's weather and space conditions, managed to track 3I Atlas from October 18th to 24, capturing images that showed the comet at magnitude 11, comparable to nearby background stars. Amateur astronomer Warachati Boonplod analyzed the satellite data and confirmed the comet was easily detectable and moving steadily through the field of view. The comet brightened rapidly as it approached perihelion, reaching an estimated magnitude 9 by October 30th, still far too faint for naked-eye observation, but significantly brighter than earlier predictions. The Solar and Heliospheric Observatory and the polarimeter to unify the corona and heliosphere satellites also caught glimpses during this window, though their data has not yet been fully analyzed. The real witnesses, the spacecraft with the best possible vantage points, orbit Mars. The European Space Agency's ExoMars Trace Gas Orbiter successfully photographed 3I Atlas on October 3rd when the comet made its closest approach to the red planet, passing just 0.19 astronomical units, or 28 million kilometers from Mars's surface. The orbiter's CASIS camera required a 5-second exposure to capture the comet, revealing just how dim it truly is, more than 50,000 times fainter than the Martian surface it usually photographs. The Mars Express orbiter also attempted observations but failed to detect the comet due to insufficient exposure time. Most intriguing of all is the Mars Reconnaissance Orbiter, equipped with the High-Resolution Imaging Science Experiment, the most powerful camera currently operating in Mars orbit. This spacecraft almost certainly captured detailed images of 3I Atlas during its Martian flyby. But here's where things get strange. Those images haven't been released. NASA's October shutdown, whether coincidental or intentional, has kept that data locked away. What exactly is happening right now, in this blind zone, in these 40 days of darkness? If 3I Atlas is simply an ancient comet, then perihelion should trigger a predictable sequence of events. The solar heating sublimating carbon dioxide and water ice from the nucleus, the expanding coma growing to hundreds of thousands of kilometers in diameter, the formation of twin tails streaming away from the sun, one made of dust pushed by solar radiation pressure, the other of ionized gas swept back by the solar wind. The comet should emerge from behind the sun in November, looking brighter, more active, with clear signs of material loss from its nucleus. Its trajectory should follow a perfect hyperbolic path, unchanged except for the gravitational influence of the sun. Amateur astronomers and professional observatories are already preparing for its reappearance in early November, when it will become visible low in the dawn sky before sunrise. But if the object is under intelligent control, if it's using this moment of invisibility to perform maneuvers that would reveal its true nature, then everything changes. An Oberth maneuver performed at perihelion would be nearly impossible to detect until weeks or months later, when astronomers could compare the object's actual trajectory to its predicted path. Any velocity change applied at the moment of closest solar approach gets amplified by the sun's gravity, making it the most efficient point for course corrections. A spacecraft attempting to maximize its energy efficiency would wait for exactly this moment, exactly this configuration. And it would do so behind the sun, hidden from observation, where no one could watch. Michio Kaku emphasized this point repeatedly in his interviews leading up to perihelion, stating that if 3I Atlas exhibited any sign of maneuvering, any deviation from its expected path, it would constitute proof of artificial origin. Avi Loeb, the Harvard astronomer who has become both celebrated and controversial for his willingness to consider extraterrestrial explanations, published a paper in July arguing that 3I Atlas shows several unusual characteristics that warrant serious investigation. He was careful to note that these anomalies don't prove alien technology, but they do make this object worthy of extraordinary attention. In an email exchange this week, Loeb told reporters that perihelion represents an acid test for determining the object's nature. If it is a natural comet held together by weak forces, the heating it experiences could cause it to disintegrate into smaller pieces, he explained. On the other hand, if 3I Atlas is an artificial construct, it might exhibit maneuverability or deploy mini-probes. Other indicators of technology could include artificial lighting or excess heat from an engine. All of these possibilities are unfolding right now, hidden behind 865,000 miles of incandescent plasma. The European Space Agency, taking a more measured approach, published a detailed FAQ about 3I Atlas in early October, addressing the speculation and controversy head-on. They confirmed that the overwhelming scientific consensus identifies 3I Atlas as a natural comet, pointing to its active coma, the detection of typical cometary molecules like cyanide and carbon dioxide, and its behavior consistent with sublimation-driven activity. They acknowledged the unusual trajectory and early activity, but argued these features, while interesting, fall within the range of natural variation seen in both solar system and interstellar comets. The ESA scientists noted that 3I Atlas is making a poor apparition from Earth's perspective, meaning it never comes particularly close to our planet and remains relatively faint throughout its passage. But this is actually normal for most comets, and shouldn't be interpreted as evidence of anything unusual. Yet even the skeptics admit that timing is remarkable. The fact that perihelion occurs during solar conjunction, rendering the comet invisible at its most active moment, strikes many as more than simple coincidence. Statistical analysis shows that solar conjunction at perihelion is relatively rare for discovered comets, though not impossible. The 5-degree inclination of 3I Atlas's orbit to the ecliptic, the plane containing Earth's orbit, means it passes through the solar system at an angle that happens to hide it from Earth during this critical phase. Some astronomers note that if the trajectory were intentionally designed to avoid observation during perihelion, it would look exactly like this. Others counter that we only notice this alignment because we happen to be observing it, a selection bias that makes coincidences seem meaningful. The numbers tell their own story. At perihelion, 3I Atlas is 1.36 astronomical units from the Sun, roughly 203 million kilometers, positioning it between the orbits of Earth and Mars. This is actually a relatively distant perihelion compared to many comets, some of which graze the Sun at distances measured in solar radii. Yet the object is still being subjected to intense heating, enough to drive vigorous sublimation of volatile ices. Its speed at perihelion peaks at 68 kilometers per second with respect to the Sun, representing the fastest velocity of its entire journey through our solar system. For comparison, Earth orbits at 30 kilometers per second, and even speedy Mercury only manages 48 kilometers per second. This extraordinary speed is a direct consequence of the comet's hyperbolic orbit, the signature of an object not bound to our Sun, an interstellar traveler just passing through. The expected brightness at perihelion, magnitude 11.5, means that even under perfect viewing conditions, only telescopes with at least 8 inches of aperture could detect it. This is not Hale-Bopp or Hyakutake, the great comets that lit up the sky in the 1990s. This is a dim, distant object that requires patience and proper equipment to observe. The rapid brightening detected by GOES 19, from magnitude 11 to an estimated magnitude 9, suggests the comet is indeed becoming more active as it approaches perihelion, consistent with increasing sublimation. But whether this represents normal cometary behavior or something more unusual won't be clear until the comet emerges from behind the Sun and can be studied properly. We are living through a moment that will be analyzed for years, perhaps decades. Either we are witnessing a perfectly natural astronomical event, a dirty snowball from another star system making its one and only passage through our cosmic neighborhood, or we are watching something far more significant unfold in secret. The 40 days of mystery stretch before and after perihelion, from October 9th, when the solar elongation dropped below 30 degrees, to November 9th, when the comet finally achieves sufficient separation from the Sun to be observable again. During this time, 3I Atlas is essentially alone with the Sun, monitored only by a few spacecraft in favorable positions, its secrets kept by 125 million miles of empty space and the blinding glare of our star. Michio Kaku's suggestion to take vacation before October 29th, who knows what will happen, now seems either prescient or premature. The answers we seek are being written right now in the darkness behind the Sun, and we won't be able to read them until the cosmic curtain lifts in November. Speed defines everything about 3I Atlas, and the numbers are staggering beyond anything we've seen before. This comet is hurtling through our solar system at 58 kilometers per second as its baseline velocity, its hyperbolic excess velocity, the speed it carries from interstellar space itself. That's 128,000 miles per hour, fast enough to cross the entire United States in less than 30 seconds, fast enough to travel from Earth to the Moon in barely an hour. But here's what makes this truly extraordinary. This velocity isn't borrowed from our sun's gravity. It's intrinsic, carried from whatever stellar system ejected this object millions or billions of years ago. When astronomers trace the trajectory of 3I Atlas backward through time and space, removing the sun's gravitational influence from the equation, the object still maintains this incredible speed, proving beyond doubt that it came from somewhere else, from the space between the stars. Oumuamua, the first confirmed interstellar visitor discovered in 2017, traveled at 26 kilometers per second relative to the local standard of rest in our galaxy. That was impressive enough, a cosmic bullet that stunned astronomers with its speed and bizarre cigar-like shape. Then came 2I Borisov in 2019, clocked at 32 kilometers per second, clearly a comet with a visible coma and tail, less mysterious than Oumuamua, but still remarkable for its interstellar origin. Now, 3I Atlas arrives moving at 58 kilometers per second, nearly double Oumuamua's velocity, almost twice as fast as Borisov, shattering all previous records for interstellar objects passing through our cosmic neighborhood. This isn't just a minor increase, it's a fundamental difference that tells us something profound about where this object came from and how it was expelled from its birth system. The physics behind these velocities reveals the violent history written into every interstellar traveler. Objects don't casually drift between star systems at these speeds. They must be accelerated, thrown out with tremendous force by gravitational encounters, stellar flybys, planetary interactions, or perhaps other mechanisms we haven't fully considered. A close encounter with a gas giant planet, for instance, can use the planet's gravity like a slingshot, flinging smaller objects out of their home systems at high velocity. Multiple such encounters, or a single very close pass by a massive star, could impart the kind of energy we see in 3I Atlas. The comet's speed suggests it experienced something dramatic in its distant past, some cosmic event that gave it the momentum to escape not just a planetary system, but an entire stellar gravitational well. But speed isn't constant in orbital mechanics. It changes with distance according to the laws discovered by Johannes Kepler 4 centuries ago, when 3I Atlas first crossed into the outer solar system in July 2025, entering the region where our sun's gravity began to noticeably affect its trajectory. It was traveling at that baseline 58 kilometers per second. As it fell deeper into the sun's gravitational well, approaching perihelion, the object accelerated continuously, converting gravitational potential energy into kinetic energy. By the time it reached its closest approach to the Sun on October 29th, just yesterday, 3I Atlas had accelerated to 68 kilometers per second, gaining an additional 10 kilometers per second from the Sun's gravitational pull. This is the fastest the comet will ever move during its passage through our solar system, the peak velocity that occurs at the moment of perihelion when the gravitational acceleration reaches its maximum. Now, as the comet swings around the Sun and heads back out toward interstellar space, it will gradually slow down as it climbs out of the Sun's gravity well, trading kinetic energy back into potential energy. By the time 3I Atlas crosses back through the outer solar system, beyond Neptune's orbit, beyond the Kuiper belt, it will have decelerated back to approximately 58 kilometers per second, the same speed it arrived with. The Sun's gravity gives and then takes back that extra velocity, like a cosmic loan that must be repaid. The object will leave our solar system with essentially the same energy it brought with it, unchanged by its brief encounter with our star, continuing its journey through the galaxy at that same tremendous baseline velocity. To put these numbers in perspective, Earth orbits the Sun at a comfortable 30 kilometers per second, fast enough to complete one circuit around our star every 365 days. Mercury, the innermost planet, races along at 48 kilometers per second in its tight orbit, the fastest planet in our solar system. 3I Atlas at perihelion moves at 68 kilometers per second, faster than any natural object permanently bound to our Sun. Only artificial spacecraft that have performed gravity assists around multiple planets, like Voyager 1 and 2 or New Horizons after its Jupiter flyby, approach these velocities relative to the Sun. And those spacecraft required careful mission planning, years of flight time, and precise gravitational maneuvers to achieve such speeds. 3I Atlas arrived with this velocity already built in, a gift or a curse from whatever happened in its distant past. The trajectory itself tells an even stranger story. 3I Atlas follows what mathematicians call a hyperbolic orbit, characterized by an eccentricity value far greater than 1. Circular orbits have eccentricity 0, elliptical orbits like Earth's have eccentricity between 0 and 1, and parabolic escape trajectories have eccentricity exactly equal to 1. Hyperbolic orbits, the paths followed by objects with more than enough energy to escape a gravitational system, have eccentricities greater than 1. Oumuamua had an orbital eccentricity of 1.2, Borisov came in at 3.4, both clearly hyperbolic, both obviously interstellar. 3I Atlas has an eccentricity of 6.137 plus or minus 0.06, the highest value ever measured for any object observed in our solar system. This number has been refined through hundreds of observations over the past 4 months and is now known with extraordinary precision. What does an eccentricity of 6.137 mean in practical terms? It means the orbit is so extremely hyperbolic that it's almost a straight line. If you plotted the path of 3I Atlas on a graph, it would look less like a curved swoosh around the Sun and more like a slight bend in an otherwise straight trajectory. The Sun's gravity barely deflects this object from its original path. Imagine shooting an arrow through a room where someone is waving a magnet. The arrow might curve slightly toward the magnet, but it's moving so fast and the magnetic force is relatively so weak that the deflection is minimal. That's 3I Atlas interacting with the Sun, barely acknowledging the gravitational pull of a star containing 99.86 of all the mass in the solar system. The comet is fundamentally not bound to our Sun, not captured, not planning to return, just passing through with barely a nod to the local gravitational authority. Backtracking the trajectory requires sophisticated computer simulations that account for the gravitational influence of every major body in the solar system and model the motion backward through time. Multiple research teams have performed these calculations, integrating the orbit backward for 10 million years, watching the virtual comet retreat through space, past the stars we see in our night sky, past the nearer stellar neighborhood, out into the thicker regions of the Milky Way's disk. The results show that 3I Atlas passed within 1 parsec, about 3.3 light-years, or 0.3 years at light speed, of approximately 93 different stars during its 10 million-year journey to our solar system. None of these encounters were particularly close in astronomical terms. No passages through planetary systems, no tight flybys that would have significantly altered the comet's trajectory. It threaded through the stellar neighborhood like a ghost, influenced but not captured by the gravitational fields of dozens of suns. The closest approach to any star during this 10 million-year journey was still about 1 parsec, roughly the distance from our Sun to the nearest stars, like Proxima Centauri, but measured to other stars scattered through the galactic disk. This suggests that 3I Atlas has been in interstellar space for an extraordinarily long time, drifting between stars without entering any planetary system, without being captured or deflected significantly, maintaining its speed and direction with remarkable consistency. The vertical velocity component, the speed at which the comet is moving perpendicular to the galactic plane, measures 18.5 kilometers per second. This is unusually high, much faster than typical stars or objects in the galactic disk. It indicates that 3I Atlas has a highly inclined orbit through the galaxy itself, regularly crossing up and down through the galactic plane, rather than moving primarily within it. This vertical motion points to the comet's origin in what astronomers call the thick disk of the Milky Way, a population of older stars with higher random velocities and more inclined orbits compared to the thin disk where our Sun resides. The thick disk contains stars that formed 7 to 14 billion years ago, when our galaxy was younger and more turbulent, when stellar velocities were higher and orbital inclinations more random. If 3I Atlas formed in the planetary system of a thick disk star, it would have been ejected billions of years ago, possibly before complex life arose on Earth, possibly before Earth itself had fully formed from the protoplanetary disk around our young Sun. The comet could be 7.6 to 14 billion years old, according to some estimates, making it potentially twice as ancient as Earth's 4.6 billion years. If this age estimate is correct, and it remains uncertain, because we can't directly measure a comet's age without sampling it, then 3I Atlas represents material from the early galaxy, a preserved sample of conditions that existed when the Milky Way was less than half its current age. The low metallicity expected in thick disk stars adds another layer to this story. Metallicity in astronomy refers to the abundance of elements heavier than hydrogen and helium, all of which are produced inside stars and distributed through space by supernova explosions. Early generations of stars formed from gas that had been enriched by only a few previous stellar generations, so they contained fewer heavy elements than stars forming today. Planetary systems around low metallicity stars would have formed from material with different chemical compositions, potentially creating comets and asteroids with unusual properties compared to solar system objects. The high carbon dioxide to water ratio observed in 3I Atlas might be a signature of this different formation environment, though other explanations are certainly possible. One of the deepest mysteries surrounding 3I Atlas is why it didn't interact more strongly with any of the 93 stars it passed during its 10 million-year journey. Even distant passages can alter a comet's trajectory slightly through gravitational perturbations. Multiple such encounters should accumulate, gradually changing the object's speed and direction. Yet 3I Atlas arrived at our solar system with a trajectory that, when traced backward, shows relatively smooth motion through the stellar neighborhood. Either the encounters were distant enough to have minimal effect, which seems likely given the closest approach distances of about 1 parsec, or the comet's high velocity carried it through each encounter so quickly that gravitational deflections remained small. High-speed objects spend less time in any given gravitational field, giving that field less opportunity to change the object's trajectory significantly. This raises a profound question that astronomers are still debating. Did the velocity of 3I Atlas change during its 10 million-year journey? The computer models assume it didn't, or changed only according to predictable gravitational interactions with the stars it passed. But what if something else happened? What if the comet encountered a dense molecular cloud, a region of interstellar gas and dust that could slow it down through friction? Such clouds are rare and diffuse, but they exist, and a passage through one could theoretically affect the comet's velocity. Alternatively, what if the comet experienced outgassing events during its interstellar journey, jets of sublimating ice propelling it like a natural rocket engine? Current theory suggests comets should be dormant in interstellar space, too cold and too far from any star to sublimate. But 3I Atlas has already surprised us with its early activity, starting at 6.4 astronomical units from the Sun, much farther than expected. Could it have been active even farther out, even in interstellar space? The speed of 3I Atlas becomes even more significant when we consider the Oberth maneuver, the orbital mechanics technique that Michio Kaku and Avi Loeb have highlighted as a potential indicator of intelligent control. In an Oberth maneuver, a spacecraft fires its engines at the moment of closest approach to a massive body at perihelion if orbiting a star. Because the spacecraft is already moving at its maximum velocity at that point, any additional velocity imparted by the engines gets magnified in terms of the total energy added to the trajectory. It's more efficient to add velocity when you're already moving fast than when you're moving slowly. An intelligent civilization wanting to maximize the efficiency of a probe's trajectory through a star system would wait for perihelion to perform any course corrections or velocity boosts. And 3I Atlas reached perihelion yesterday at the moment when it was moving fastest, at precisely 68 kilometers per second, during the 40-day window when no Earth-based telescope could observe what was happening. If the comet emerges from behind the Sun with more velocity than expected, with a trajectory that deviates from the predictions based purely on gravitational effects, that would constitute evidence of propulsion, of intelligent control, of technology. Astronomers will be watching intently when 3I Atlas becomes visible again in November, carefully measuring its position and velocity, comparing observations to predictions, looking for any discrepancy that would indicate something extraordinary occurred during perihelion. The difference between a natural comet and an alien spacecraft could come down to a velocity change of just a few kilometers per second, a small number in absolute terms, but a huge signal in its implications. Natural processes, specifically outgassing jets, can change a comet's velocity, but those changes are typically small, irregular, and difficult to control precisely. A deliberate maneuver would show up as a clean, directed velocity change that couldn't be explained by asymmetric sublimation or fragment ejection. The scientific consensus remains firmly on the side of natural explanations. 3I Atlas shows all the hallmarks of a comet: a coma created by sublimating ice, spectroscopic detection of cometary molecules like cyanide and carbon dioxide, brightness variations consistent with gas and dust production, and behavior that matches theoretical models of comet activity. Its extreme velocity, while record-breaking, falls within the range of what gravitational dynamics can produce through planetary ejection and stellar encounters. The high eccentricity is unusual, but not inexplicable. Every anomaly has potential natural explanations, even if some of those explanations require refining our models or invoking rare circumstances. But the speed of this object, that incredible 58 to 68 kilometers per second, ensures that whatever 3I Atlas turns out to be, it will remain one of the most extraordinary visitors our solar system has ever received. And we're about to find out if that velocity stayed constant or changed in ways we can't yet explain. The trajectory of 3I Atlas violates one of the most basic assumptions about random motion through space, and this violation sits at the heart of the controversy surrounding this object. When astronomers first calculated its orbit in early July 2025, they discovered something profoundly unsettling. The comet is traveling at an orbital inclination of 175 degrees, which means it's moving retrograde, backward relative to the direction planets orbit the Sun, and it's tilted just 5 degrees from the ecliptic plane. To understand why this matters, you need to grasp what the ecliptic actually represents. The ecliptic is the flat disk, the geometric plane containing Earth's orbit around the Sun, and with minor variations, all the major planets orbit within this same plane, tilted by only a few degrees from each other. Mercury has the highest inclination at 7 degrees, Venus sits at 3.4 degrees, and Earth defines 0 by definition. This isn't coincidence, it's a direct consequence of how our solar system formed from a rotating disk of gas and dust 4.6 billion years ago. Interstellar space, by contrast, is three-dimensional in every sense. Objects drifting between stars can approach from any direction, any angle, with equal probability. The galaxy itself is a flattened disk about 1,000 light-years thick and 100,000 light-years across, so there's a slight statistical bias toward objects moving within the galactic plane, but even that bias is minimal for high-velocity objects like 3I Atlas, with its unusual vertical motion component. When you calculate the probability that a randomly approaching interstellar object would, by pure chance, align itself within 5 degrees of our solar system's ecliptic plane, the numbers become uncomfortable. Space is vast, directions are infinite, and the ecliptic represents an infinitesimally small slice of all possible approach vectors. Yet here comes 3I Atlas, threading through space at precisely the angle that takes it on a tour of the inner planets, passing close to Mars, then swooping by Venus, approaching Earth, and eventually reaching Jupiter. Avi Loeb seized on this alignment in his controversial paper published July 16th, arguing that the trajectory shows signs of being improbable for a natural object. His statistical analysis suggested that the odds of such precise ecliptic alignment occurring by chance were low enough to warrant serious consideration of artificial guidance. Other astronomers, including David Kipping and Scott Manley, quickly pointed out flaws in Loeb's statistical methodology, arguing he had failed to properly account for observational bias and had cherry-picked unusual features while ignoring the many ordinary characteristics 3I Atlas displays. The scientific community's overwhelming response was skepticism bordering on exasperation, with Chris Lintott expressing disappointment that Loeb's speculation was distracting from the genuine scientific work being done by dozens of research teams studying the comet. But even critics of Loeb's interpretation acknowledge the trajectory is unusual. Oumuamua approached the solar system from the direction of the constellation Lyra, coming in at a steep angle and making only a brief, distant pass through the inner solar system before departing. Borisov arrived from the direction of Cassiopeia, also at a significant angle to the ecliptic, swooping through and departing without closely approaching any planet. Both followed what we might call drive-by trajectories, coming from one direction in three-dimensional space, curving around the Sun under gravitational influence, and departing in a different direction. 3I. Atlas is different, fundamentally different in a way that's geometrically striking when you plot its path. It's coming at the solar system almost edge-on, moving retrograde in an orbit inclined 175 degrees, which is equivalent to saying it's moving backward at an inclination of 5 degrees. This retrograde, nearly planar trajectory takes it through the ecliptic plane itself, the region where all the planets congregate, maximizing its opportunities for close planetary approaches. The timeline of these planetary encounters reads like an itinerary. On October 3rd, just 4 weeks ago, 3I Atlas passed Mars at a distance of 0.19 astronomical units, roughly 28 million kilometers, the closest approach to any planet during its entire journey through our solar system. This wasn't a distant flyby, it was close enough that Mars orbiters could photograph the comet, close enough that gravitational perturbations from Mars slightly altered 3I Atlas's trajectory, close enough that if the comet had shed any debris, that debris could theoretically have been captured by Martian gravity. Then came perihelion on October 29th, the Sun itself at 136 astronomical units, the moment of maximum heating and activity. Next comes Venus on November 3rd, just 5 days from now, at a distance of 0.65 astronomical units, or 97 million kilometers, substantially closer than the Earth-Sun distance. The comet will pass Earth's orbit on December 19th, though Earth itself will be elsewhere in its orbit at that time, leaving the actual Earth-comet distance at 1.80 astronomical units. Finally, on March 16, 2026, comes the Jupiter flyby at 0.36 astronomical units, or 54 million kilometers, close enough that Jupiter's immense gravity will noticeably deflect the comet's outbound trajectory. This sequence, Mars, Sun, Venus, Earth, Jupiter, represents almost a grand tour of the inner solar system and its largest planet. If you were designing a probe to survey our planetary system, if you wanted to gather data on multiple worlds during a single passage, this trajectory would be extraordinarily efficient. One could argue it's optimal, or at least near optimal, given the constraints of hyperbolic geometry and the fixed positions of the planets. But here's the problem with that argument. The planets are moving targets. Earth completes an orbit every 365 days, Mars every 687 days, Jupiter every 12 years. The positions of the planets when 3I Atlas arrives are essentially random from the perspective of an object that's been traveling for millions of years through interstellar space. For the comet to pass close to Mars on October 3rd, it had to arrive at the precise moment when Mars was at the right position in its orbit, and the same logic applies to every other planetary encounter. This timing requirement multiplies the improbability significantly. Scott Manley, a popular science communicator with a background in astronomy, created a detailed video analyzing Loeb's statistical claims and demonstrating where the analysis had gone wrong. Manley showed that when you properly account for the fact that we're more likely to discover and carefully observe unusual objects, many of the apparent anomalies fade into statistical noise. David Kipping, an astronomer at Columbia University specializing in exoplanets and statistical analysis, performed independent calculations and reached similar conclusions, arguing that 3I Atlas, while interesting, doesn't show clear evidence of artificial guidance. Their work represents the mainstream scientific view. This is a natural comet that happened to arrive at an unusual angle, and we're pattern matching on features that seem meaningful but are actually within the range of random variation. The European Space Agency's position, articulated in their October FAQ about 3I Atlas, acknowledges the unusual trajectory but emphasizes that unusual doesn't mean impossible or unnatural. They point out that we've only observed 3 interstellar objects total, a sample size far too small to establish what's typical versus what's rare. Oumuamua and Borisov showed us 2 different trajectories, both different from each other, both different from 3I Atlas. With such limited data, we simply don't know the distribution of interstellar object trajectories. It's entirely possible that ecliptic-aligned approaches are more common than we'd naively expect, perhaps because objects ejected from planetary systems tend to be ejected in the plane of those systems, and planetary system planes might have some weak alignment with the galactic disk. Or perhaps there's no deeper explanation. Perhaps 3I Atlas just got lucky, arriving at the right angle through pure chance. But let's explore the other possibility, the one that Loeb and Kaku find compelling enough to discuss publicly, despite the ridicule it attracts. If 3I Atlas is under intelligent control, if it's a probe sent by another civilization to study our solar system, what would its trajectory look like? It would need to approach from interstellar space, which means it would arrive with high velocity, probably on a hyperbolic trajectory, unless it planned to use our sun's gravity for deceleration. It would want to pass close to multiple planets to gather data, which means it would need to travel through the ecliptic plane rather than diving steeply through the solar system. It would time its arrival to coincide with favorable planetary positions, or it would adjust its approach trajectory during the inbound leg of its journey to ensure optimal encounters. And if it wanted to perform an Oberth maneuver at perihelion, if it wanted to use the sun's gravity to boost its velocity or change its outbound trajectory, it would do so at the moment of closest approach, when Earth-based observation is impossible due to solar conjunction. The ExoMars Trace Gas Orbiter observations from October 3rd provide the most detailed images we have of 3I Atlas during its Martian flyby. The orbiter's Cassis camera captured the comet as a faint smudge against the background stars, requiring a 5-second exposure to gather enough light. The image shows a clearly defined coma, the cloud of gas and dust surrounding the nucleus, extended and slightly asymmetric in shape. This coma is evidence of active sublimation, of ice turning to gas, of material being ejected from the comet's surface. It's exactly what you'd expect to see from a natural comet at that distance from the Sun. Mars Express, equipped with different instrumentation, attempted simultaneous observations but couldn't detect the comet due to its shorter exposure times, confirming just how dim 3I Atlas truly is. The failure to detect it with Mars Express serves as an important control, showing that the ExoMars detection was genuine and that the comet's faintness wasn't an artifact of observation. Most frustrating for those hoping to resolve the natural versus artificial debate is the Mars Reconnaissance Orbiter data that remains unreleased. MRO carries HiRISE, the high-resolution imaging science experiment, capable of resolving features just meters across on the Martian surface. Pointed at 3I Atlas during the October 3rd flyby, HiRISE could potentially have captured images detailed enough to see structure in the coma, asymmetries in the dust distribution, perhaps even hints of the nucleus itself if observing conditions were optimal. But NASA's partial government shutdown in October meant that data processing and release were delayed, and as of late October, those observations haven't been made public. Conspiracy theorists seized on this delay as evidence of a cover-up, suggesting the images show something NASA doesn't want revealed. More prosaically, government shutdowns routinely delay data releases, And there's no particular reason to suspect anything unusual about this delay beyond bureaucratic dysfunction. Chris Lintott, an astronomer at the University of Oxford and co-host of the BBC's Sky at Night program, has been particularly vocal in criticizing the speculation surrounding 3I Atlas. In interviews and social media posts, he's expressed frustration that Loeb's hypothesis, despite lacking strong evidentiary support, generates headlines that overshadow the careful work being done by observational astronomers characterizing this genuinely interesting object. Lintott emphasizes that overwhelming consensus is that it is a comet, backed by spectroscopic detections of cometary molecules, observations of a growing coma, and behavior entirely consistent with sublimation-driven activity. He acknowledges the trajectory is unusual, but argues that one unusual feature among hundreds of measurements doesn't constitute evidence for extraordinary claims. The trajectory mystery, ultimately, comes down to probabilities and prior assumptions. If you start with the assumption that intelligent extraterrestrial civilizations are extremely rare or non-existent, then any natural explanation for 3I Atlas, no matter how improbable, will seem more likely than artificial guidance. If you start with the assumption that technological civilizations are common and might reasonably send probes to explore other star systems, then unusual features like the ecliptic alignment start to carry more weight as potential evidence. Science generally favors the first approach, demanding extraordinary evidence for extraordinary claims, and the evidence for 3I Atlas remains, at present, well within the realm of what natural processes can produce. But the questions persist, and they won't be fully answered until the comet emerges from behind the Sun, and we can check whether its trajectory changed during perihelion, whether something happened in those 40 dark days that would force us to reconsider everything we think we know. Something strange happened to 3I Atlas months before anyone knew it was there, and the evidence was hiding in data that wouldn't be analyzed until long after the comet's official discovery. The Transiting Exoplanet Survey Satellite, TESS, designed to find planets around distant stars by monitoring millions of stars for tiny brightness dips, happened to scan the region of sky containing 3I Atlas from May 7th to June 3rd, 2025. At that time, the comet was still 6.4 astronomical units from the Sun, farther out than Jupiter, in the cold outer reaches where most comets remain dormant, frozen solid, showing no signs of activity. But TESS recorded something, a faint, moving object that brightened substantially during the observation period. When astronomers later went back through the archived data after the comet's official discovery on July 4th, they realized they were looking at pre-discovery observations, images of 3I Atlas taken 2 months before anyone knew to look for it. And those images revealed a mystery that still hasn't been adequately explained. The Vera Rubin Observatory, still in its commissioning phase but already conducting test observations, also captured 3I Atlas in late June and early July 2025, from June 21st to July 3rd. The Zwicky Transient Facility in California photographed the comet from May 22nd to June 24th. Israel's Weizmann Observatory recorded what may be the earliest observation on May 21st. All of these pre-discovery detections became apparent only after July 4th, when the Atlas survey in Chile officially discovered and reported the comet, triggering alerts that sent astronomers scrambling to their archives to find earlier images. What they found was a comet that had been visible for months, gradually brightening as it approached the Sun, but displaying behavior that didn't quite match predictions. If the Vera Rubin Observatory had begun its survey operations just 2 weeks earlier, it would have discovered 3I Atlas before Atlas did, potentially giving the scientific community more time to prepare observations of this rare interstellar visitor. The most perplexing finding came from analyzing the brightness changes recorded across all these early observations. As a comet approaches the Sun, it receives more solar heating, which causes volatile ices on and near its surface to sublimate more vigorously, producing more gas and dust, making the coma larger and brighter. Astronomers have well-established models for predicting how a comet's brightness should increase with decreasing solar distance, based on the inverse square law of radiation and empirical relationships derived from observing thousands of comets over centuries. These models predicted that 3I Atlas should brighten by a factor of approximately 1.5 times as it moved from 6.4 astronomical units in early May to closer distances in June. Instead, observations showed the comet brightened by a factor of 5, more than 3 times as much as expected. This wasn't a small discrepancy. It was a dramatic deviation that demanded explanation. Several hypotheses immediately presented themselves. The simplest was measurement error. Perhaps the early TESS observations had underestimated the comet's brightness due to its faintness and the challenges of detecting a moving object in data optimized for stellar photometry. But multiple independent observations from different telescopes and instruments all told the same story. 3I Atlas was brightening faster than it should. The second hypothesis was an outburst, a sudden explosive release of gas and dust that many comets experience as subsurface ice pockets are exposed to sunlight and rapidly vaporize. Outbursts can temporarily increase a comet's brightness by factors of 10 or more, creating dramatic flares that fade over days to weeks. But the brightening of 3I Atlas appeared more gradual and sustained, not matching the typical signature of an outburst event. No one reported observing a distinct outburst, though the sparse early observations left gaps in coverage where one could have occurred unnoticed. The third hypothesis, and the one that's gained the most scientific traction, involves the unusual composition of 3I Atlas, and specifically its extraordinarily high carbon dioxide content. Carbon dioxide ice sublimates, transitions directly from solid to gas, at much lower temperatures than water ice. Where water ice requires temperatures above about 180 Kelvin to sublimate efficiently, carbon dioxide ice begins sublimating vigorously at temperatures around 80 Kelvin. At 6.4 astronomical units from the Sun, where TESS first observed the comet in May, the equilibrium temperature on the comet's surface would be approximately 120 to 140 Kelvin, cold enough to keep water ice frozen solid, but warm enough to sublimate carbon dioxide. If 3I Atlas has a surface rich in carbon dioxide ice, as subsequent observations strongly suggest, then it would begin showing activity much farther from the Sun than a typical water-dominated comet. This early activity could drive faster than expected brightening as the comet rapidly builds its coma in the weeks and months leading up to perihelion. The James Webb Space Telescope settled at least part of the composition question when it observed 3I Atlas on August 6, 2025, using its near-infrared spectrograph. JWST's spectrum revealed emission lines from carbon dioxide, water, carbon monoxide, and carbonyl sulfide, allowing astronomers to measure the production rates of each molecule. The results were striking. 3I Atlas was emitting 129 kilograms of carbon dioxide per second, but only 6.6 kilograms of water per second, yielding a carbon dioxide to water ratio of approximately 8 to 1. This is one of the highest CO2 to H2O ratios ever measured in any comet, interstellar or otherwise. For comparison, typical solar system comets show ratios closer to 110 or 1/100, with water being the dominant volatile by far. Only C2016 R2 Pan-STARRS, an extremely peculiar comet discovered in 2016, shows a similarly high carbon dioxide abundance. The fact that 3I Atlas resembles one of the most anomalous comets in our own solar system raises fascinating questions about comet formation conditions in other stellar systems. Carbon monoxide production measured at 14 kilograms per second, giving a CO to H2O ratio of about 1.4 to 1, which is less unusual but still on the high end of normal for comets. Carbonyl sulfide, a rare molecule in comets, was detected at 0.43 kilograms per second, providing a valuable clue about sulfur chemistry in the comet's nucleus. The JWST spectrum also showed absorption features indicating the presence of fine water ice grains, smaller than 1 micrometer in size, suspended in the coma. These tiny ice particles were likely ejected from the nucleus by the outgassing carbon dioxide and carbon monoxide, carried along with the gas flow like dust caught in a wind. The ice is probably amorphous rather than crystalline, though distinguishing between the two forms from spectroscopic data remains challenging. Amorphous ice forms when water vapor condenses in extremely cold conditions without time to organize into crystalline structure and it can trap other volatiles like carbon dioxide and carbon monoxide in molecular cages, releasing them suddenly when the ice warms and transitions to crystalline form. The Swift Observatory added another crucial piece to the puzzle on July 31st and August 1st, when it tentatively detected water vapor and hydroxyl radicals, the OH molecule that forms when ultraviolet light breaks apart water molecules in the comet's coma. But here's what made this detection particularly interesting. The data suggested the water vapor wasn't coming directly from the nucleus. Instead, the Swift observations indicated that water ice grains were being ejected from the nucleus and then sublimating at distances between 4,000 and 10,000 kilometers from the nucleus itself. This delayed sublimation makes sense if the water ice is being lifted off the nucleus by carbon dioxide outgassing rather than sublimating due to its own vapor pressure. The CO2 jets blast material off the surface, including water ice particles that are too cold to sublimate immediately but warm up as they travel through the coma, eventually turning to gas thousands of kilometers from their source. This mechanism has been observed in other comets, but rarely so clearly documented. The Sphere-X Space Observatory confirmed the high carbon dioxide abundance in mid-August observations, though it lacked the sensitivity to detect water vapor or carbon monoxide. Sphere-X measured the carbon dioxide coma extending to a radius of 348,000 kilometers, a vast cloud of gas larger than the planet Jupiter. This enormous size reflects both the vigorous production rate and the low density of gas in the coma, which allows molecules to travel far from the nucleus before colliding with other molecules or being dissociated by solar ultraviolet radiation. The coma's size also explains why the comet appears brighter than its small nucleus would suggest. We're seeing reflected sunlight from an immense cloud of gas and dust, not from the tiny nucleus itself. But the composition story gets stranger when we consider what's missing from 3I Atlas's spectrum. The Very Large Telescope observations from July through August specifically looked for atomic oxygen, dicarbon, tricarbon, and amino radicals, none of which were detected. The MDM Observatory in Arizona also searched for dicarbon and tricarbon, finding nothing. These carbon chain molecules are common in many comets and are thought to be produced by the ultraviolet breakup of larger organic molecules. Their absence suggests that 3I Atlas is depleted in certain types of organic compounds, making it one of the most carbon chain depleted comets ever observed. This depletion could reflect unusual formation conditions in the comet's birth system, perhaps around a star with different ultraviolet output, or in a protoplanetary disk with different chemical composition. Or it could indicate that the comet formed at an unusual location within its birth system, perhaps in an outer, colder region where certain chemical reactions couldn't occur efficiently. The negative polarization measurements add yet another layer to the compositional mystery. Polarimetry, the measurement of polarized light reflected from an object, provides information about the size, shape, and composition of dust grains in the coma. Observations by the Very Large Telescope, the Nordic Optical Telescope, and Bulgaria's Rozhen Observatory in July and August 2025 showed that sunlight reflected from 3I Atlas's coma exhibited negative polarization at small phase angles, the angle between the Sun, the comet, and the observer. This negative polarization is unusual, but not unprecedented. It's also seen in trans-Neptunian objects, the icy bodies orbiting beyond Neptune in the distant reaches of our solar system. The polarization signature suggests that the coma contains a mixture of icy particles and dark, carbon-rich organic material called tholins. Tholins form when ultraviolet radiation or cosmic rays process simple organic molecules like methane and nitrogen, creating complex reddish-brown polymers. Their presence in 3I Atlas implies that the comet's surface has been heavily processed by radiation during its long journey through interstellar space. The coma size measurements tracked throughout the summer show the rapid development of activity as 3I Atlas approached the Sun. On June 21st, when the comet was first observed by Vera Rubin, the coma diameter measured approximately 13,040 kilometers. By July, just 11 days later, the diameter had expanded to 18,760 kilometers, a 44 increase. The Gran Telescopio Canarias in Spain measured an even larger, slightly elongated coma of 26,400 by 24,700 kilometers on July 2nd. By mid-August, when Spherex observed, the CO2 coma had expanded to a radius of 348,000 kilometers, nearly 250,000 miles, creating one of the largest structures in the inner solar system. This rapid growth reflects the accelerating sublimation as solar heating intensified with decreasing distance. The mystery of the five-fold brightness increase remains incompletely resolved. Carbon dioxide sublimation can account for early activity and might explain faster than predicted brightening if the comet's surface is dominated by CO2 ice rather than water ice. But does this fully explain a factor of 5 discrepancy between prediction and observation? Some astronomers remain skeptical, suggesting that an unobserved outburst or a particularly unusual surface composition might be needed to fully account for the observations. Others argue that our models for comet brightness evolution are based almost entirely on solar system comets, which are predominantly water-dominated, and that applying these models to a carbon dioxide-rich interstellar comet introduces uncertainties large enough to explain the discrepancy. The truth likely lies somewhere in this complexity. 3I Atlas is genuinely unusual in its composition. This unusual composition drives behavior that our standard models don't predict well, and the early observations captured this unusual behavior in a way that highlights just how different interstellar comets can be from their solar system cousins. As 3I Atlas emerges from behind the Sun in November and can be studied again with ground-based telescopes, astronomers will be watching carefully to see if its brightness evolution continues to surprise or settles into more predictable behavior now that the carbon dioxide-rich outer layers may have been stripped away by solar heating. Every astronomy textbook teaches the same fundamental lesson about comet tails. They always point away from the Sun, blown back by solar wind and radiation pressure like a cosmic windsock showing the direction of stellar gales. This is one of the most reliable and easily observable features of comets, visible even to ancient civilizations who tracked these hairy stars across their skies. The dust tail, swept back by photons physically pushing on microscopic particles, and the ion tail, dragged away by the solar wind's magnetic field catching charged molecules, both stream behind the comet as it orbits, creating the beautiful displays that have inspired wonder and fear throughout human history. So when astronomers observing 3I Atlas in July and August 2025 documented a prominent feature extending from the coma toward the Sun rather than away from it, they knew they were seeing something unusual, something that demanded careful explanation before speculation spiraled into sensationalism. The Nordic Optical Telescope on La Palma in the Canary Islands captured the clearest images of this sun-facing plume on July 2, 2025, when 3I Atlas was approximately 4.3 astronomical units from the Sun. The images showed the comet's coma distinctly elongated westward in the direction of the Sun's position in the sky, creating what looked superficially like a tail pointing the wrong way. Other observatories confirmed the feature throughout July and into early August, making it clear this wasn't an observational artifact or processing error. The plume was real, substantial, and oriented in a direction that seemed to violate basic cometary physics. Social media erupted with speculation, with Avi Loeb supporters pointing to the anomaly as potential evidence of controlled maneuvering, of artificial jets steering the object through space. But veteran comet observers recognized the phenomenon. They'd seen it before in other unusual comets, and they understood the physics that creates sun-facing plumes without invoking alien technology. The mechanism is actually straightforward once you understand the three-dimensional geometry of cometary activity. A comet nucleus, unlike a planet, is typically an irregular rotating lump of ice and rock just a few kilometers across. When the Sun heats this nucleus, sublimation doesn't occur uniformly across the surface. The side facing the Sun, the subsolar point and surrounding region, receives the most intense heating and sublimates much more vigorously than the night side or the regions near the terminator where sunlight strikes at oblique angles. This creates an asymmetric distribution of outgassing, with the strongest jets erupting from the sunward hemisphere. Those jets carry dust and ice particles along with the sublimating gas, creating plumes that initially move outward from the surface in the direction perpendicular to where they're ejected. If the nucleus is rotating slowly, or if we're viewing it from a particular angle, we can see these sunward hemisphere plumes as features that appear to point toward the sun. There's also a directional component related to the comet's orbital motion. 3I Atlas is moving at tremendous velocity, 58 to 68 kilometers per second, depending on its distance from the sun, and this velocity has a direction, a specific vector, through three-dimensional space. Material ejected from the nucleus carries the nucleus's orbital velocity plus the velocity imparted by the outgassing jets. When dust and gas are ejected from the sunward face while the comet is traveling rapidly, the result can be a plume that appears to stretch both toward the sun and in the direction of motion, creating complex geometries that depend critically on viewing angle. From Earth's perspective in July and August, as 3I Atlas approached perihelion, this geometry produced the observed sun-facing plume. The phenomenon has been documented in other comets, most notably C-2014 UN-271, Bernardinelli-Bernstein, the giant comet discovered in archival data and studied intensively as it slowly approaches its perihelion decades from now. Bernardinelli-Bernstein displayed similar sun-facing features at great distances from the sun, confirming that this behavior, while uncommon, falls within the range of natural cometary activity. But the story of 3I Atlas's plume doesn't end with the sun-facing phase. Something changed dramatically in late August, and this change is what makes the sequence of observations particularly intriguing. On August 26th, observations showed that the sun-facing plume, while still visible, had weakened considerably. The coma no longer displayed the pronounced westward elongation seen in July. The inner coma, the region within about 5 arcseconds of the nucleus, still showed asymmetry with a fan-shaped brightness distribution, brighter on the sun-facing side, but the dramatic plume structure had faded. Then, over the following weeks, as 3I Atlas continued its approach toward perihelion, a more conventional anti-solar tail began to develop, growing stronger and more obvious with each set of observations. By mid-September, the comet sported a clear tail pointing away from the sun, the expected configuration that matches textbook descriptions and millennia of observational history. The Hubble Space Telescope, turning its powerful cameras toward 3I Atlas in July 2025, captured what may have been the first hints of this anti-solar tail development. Hubble's images showed a faint, broad tail extending eastward from the nucleus, pointing away from the sun's direction. But there was a complication with interpretation. The tail appeared foreshortened, compressed in apparent length, suggesting it was pointing almost directly away from Earth as well as away from the sun. This geometric configuration made it difficult to measure the tail's true three-dimensional extent, but clearly showed that material was being swept back by solar radiation pressure even while the sun-facing plume dominated the visual appearance of the coma. The comet was simultaneously developing both structures, the unusual sun-facing plume from active outgassing on the subsolar hemisphere and a conventional anti-solar tail from dust particles released across the entire coma being pushed by photon pressure. By August 27th, observations from the Gemini South Telescope in Chile documented the anti-solar tail extending approximately 30 arcseconds, equivalent to roughly 56,000 kilometers at the comet's distance. The James Clerk Maxwell Telescope in Hawaii measured the tail at 50 arcseconds, about 100,000 kilometers, on September 15th. The tail was growing, both because the comet was producing more dust as it heated up, and because the existing dust was being pushed farther from the nucleus by accumulating radiation pressure. The transition from sun-facing plume dominance to anti-solar tail dominance over the span of a month reflects the changing balance of forces and processes acting on the coma. As the comet approached closer to the sun, as heating intensified and activity increased, the outgassing became more vigorous and perhaps more uniform across the illuminated hemisphere, reducing the stark asymmetry that created the sun-facing plume. Simultaneously, The increasing intensity of solar radiation provided stronger pressure to sweep dust into a conventional tail structure. Avi Loeb's interpretation of these observations predictably diverged from the mainstream scientific consensus. In interviews and social media posts during August and September, he suggested that the changing tail morphology could indicate controlled maneuvering, that the shift from sun-facing to anti-solar orientation might reflect deliberate attitude changes of a spacecraft rather than natural evolution of cometary activity. The European Space Agency, anticipating this line of speculation, addressed it directly in their FAQ document about 3I Atlas, noting that anti-tails, sun-facing plumes, and other unusual tail configurations are rare but well-documented natural phenomena in comets. They emphasized that C-2014 UN-271 Bernardinelli-Bernstein and several other comets have displayed similar features without any indication of artificial control, and that the physics of asymmetric outgassing and viewing geometry fully explains what's observed in 3I Atlas. The dust ejection rates calculated from the observations provide quantitative insight into the physical processes at work. In July 2025, when the sun-facing plume was most prominent, astronomers estimated that 3I Atlas was ejecting small particles, approximately 1 micrometer in diameter, at velocities around 22 meters per second, with a mass loss rate of about 6 kilograms per second. Larger particles, around 100 micrometers in size, were being ejected more slowly at roughly 2 meters per second, but at higher mass rates of 60 kilograms per second. The total dust production of approximately 66 kilograms per second placed 3I Atlas in the same activity range as 2I Borisov, when that interstellar comet was at comparable solar distances. These numbers confirm that 3I Atlas is a genuinely active comet producing substantial amounts of material, not a dormant rock or a metallic spacecraft merely reflecting sunlight. The velocity distribution of ejected particles reveals details about the outgassing process itself. Small particles are ejected faster because they have less inertia and are more easily accelerated by the expanding gas, while larger particles are dragged along more slowly, like pebbles carried by a stream versus boulders that barely move. The relatively low ejection velocities, measured in tens of meters per second, are consistent with sublimation-driven outgassing from a comet nucleus with weak gravity. For comparison, escape velocity from a 1-kilometer diameter comet nucleus is only about 1 meter per second, so even the slowest ejected particles have more than enough velocity to leave the nucleus permanently, populating the coma and eventually drifting into the tail. If these particles were being ejected by mechanical means, by jets or thrusters on a spacecraft, we'd expect to see much higher velocities and probably a different size distribution. The comparison to C-2014 UN-271 Bernardinelli-Bernstein is particularly instructive because that comet has been so well studied despite its enormous distance from both the Sun and Earth. Bernardinelli-Bernstein, with an estimated nucleus diameter of about 130 kilometers, is one of the largest comets ever discovered, and it's been active since first detected at distances beyond 20 astronomical units from the Sun. Its activity at such extreme distances requires sublimation of ultravolatile ices like carbon monoxide or even nitrogen, substances that remain frozen at temperatures where water and carbon dioxide are completely solid. The sun-facing features observed in Bernardinelli-Bernstein provided a template for interpreting similar features in other comets, including 3I Atlas. The physics is universal. Asymmetric heating drives asymmetric outgassing, and viewing geometry determines what we see from Earth. The fact that multiple comets in our own solar system display these features strongly supports natural explanations for what we observe in the interstellar visitor. Yet the abruptness of the transition in late August remains intriguing even within natural explanations. What changed on the comet's surface or in its activity pattern to cause the sun-facing plume to fade while the anti-solar tail strengthened? One possibility is that the comet's rotation axis is oriented such that different regions of the surface became more or less active as the subsolar point migrated with changing sun-comet geometry. Another possibility is that a particular active region, perhaps an exposed patch of especially volatile ice, exhausted itself through sustained outgassing, causing the asymmetry to diminish. Alternatively, the increasing overall activity level as the comet approached perihelion might have smoothed out earlier asymmetries, making the coma more spherically symmetric and therefore less likely to produce distinct plumes in any particular direction. All of these scenarios are natural and have been observed in other comets to varying degrees. The rotation period of 3I Atlas, measured at approximately 16 hours with some uncertainty, means the comet completes one full rotation every 2/3 of an Earth day. This relatively fast rotation should, in principle, create fairly symmetric outgassing as all regions of the surface cycle through day and night on a timescale of hours. The fact that such pronounced asymmetry was visible at all suggests strong non-uniformity in the surface composition or structure, perhaps active regions concentrated on particular parts of the nucleus. As these regions evolved, sublimating away or becoming covered with dust, the asymmetry would naturally change. The transition from sun-facing plume to anti-solar tail simply represents the time evolution of these surface properties, combined with increasing activity levels as the comet heated up in its approach to perihelion. By the time 3I Atlas entered solar conjunction in late October and vanished behind the Sun from Earth's perspective, the comet presumably sported a well-developed anti-solar tail, the conventional configuration we expect. The sun-facing plume had become a historical curiosity, documented in the early observations but no longer dominating the appearance. When the comet emerges in November and becomes observable again, astronomers will be watching to see if the tail has grown even longer, if new asymmetries have developed, if the nucleus shows signs of fragmentation or unusual activity patterns. The 40 days of darkness at perihelion represent a gap in our knowledge, a period when the most intense activity was occurring completely hidden from Earth-based observation. Whatever changes happened during that time will become apparent only when 3I Atlas reappears in the dawn sky, trailing a tail that tells the story of what happened when no one was watching. On July 20, 2025, astronomers using the Very Large Telescope in Chile's Atacama Desert pointed their instruments at 3I Atlas and detected something that shouldn't exist in isolation: atomic nickel vapor streaming from the comet's nucleus, glowing in the ultraviolet spectrum as sunlight excited the metal atoms into higher energy states. Nickel in comets isn't particularly surprising. Many solar system comets emit small amounts of metallic vapors when heated by the sun, their surfaces containing trace amounts of iron, nickel, sodium, and other elements incorporated during formation billions of years ago. What made the 3I Atlas detection extraordinary was what wasn't there alongside the nickel: iron. Everywhere we look in the universe, nickel and iron appear together in nearly fixed proportions, forged together in the cores of dying stars, expelled together in supernova explosions, incorporated together into planets and asteroids and comets. They're cosmic siblings, inseparable by the universal laws of stellar nucleosynthesis. Yet here was 3I Atlas, clearly emitting nickel but showing no detectable iron emission, violating one of the most fundamental chemical patterns in astrophysics. The detection came from spectroscopy, the technique of spreading light into its component wavelengths to identify the unique fingerprints of different elements and molecules. When atoms absorb ultraviolet radiation from the sun, they transition to excited states, then fall back to lower energy levels by emitting specific wavelengths of light. Each element has its own unique pattern of emission lines, as distinctive as a barcode, allowing astronomers to identify precisely what substances are present in a distant object's atmosphere or coma. The VLT spectrum on July 20th showed clear emission lines from neutral nickel atoms, designated Ni in spectroscopic notation, at wavelengths around 341 nanometers in the ultraviolet. The expected iron emission lines, FE-WMEs, which should appear at wavelengths around 372 and 382 nanometers, were completely absent. The telescope's sensitivity was more than adequate to detect iron at the concentrations typically found alongside nickel, so the absence represented a genuine chemical anomaly, not an observational limitation. The mystery deepened as observations continued through late July and into August. On July 4th and then again on August 21st, the VLT team conducted follow-up spectroscopy to track how the nickel emission evolved as the comet approached the Sun. They found that the nickel emission was increasing rapidly and steadily, in the words of their published reports, strengthening day by day as solar heating intensified and sublimation accelerated. The production rate climbed from barely detectable levels in early July to approximately 4.6 grams per second, plus or minus 0.7 grams by August 24. For context, a gram per second might sound small, but sustained over hours and days, it adds up to tons of material, and 4.6 grams per second means 3I Atlas was losing nearly 400 kilograms of nickel every 24 hours at its peak observed emission rate. This is comparable to the nickel emission rates measured in active solar system comets at similar heliocentric distances, suggesting the process producing nickel in 3I Atlas operates at similar efficiency to whatever process produces it in local comets. Then, on August 21st, something changed. The VLT spectrum on that date suddenly showed both nickel and iron emission lines. After more than a month of observations showing only nickel, iron had appeared seemingly out of nowhere. The iron emission wasn't weak or tentative, it was clear and strong, bringing the nickel-to-iron ratio back into the range typically observed in comets. Whatever mechanism had been suppressing or hiding the iron emission had either ceased operating or had been overwhelmed by the increasing activity levels as the comet heated up. The simultaneous detection of iron coincided with another significant finding. The Lowell Observatory in Arizona reported a tentative detection of cyan molecules on August 14th. The VLT observations confirmed the cyanide detection on August 21st, the same day iron appeared, suggesting that multiple changes in the comet's activity or composition were happening nearly simultaneously as 3I Atlas crossed some threshold in solar heating. The nickel emission rate on August 21st, measured at 4.6 grams per second, represented the peak of observations before the comet entered the solar conjunction phase and became too close to the Sun for ground-based spectroscopy. Extrapolating forward, the emission rate would have continued increasing as the comet approached perihelion on October 29th, potentially reaching tens of grams per second during the peak heating phase that no Earth-based telescope could observe. The concentration of nickel in the coma increased steadily as the comet moved from 4.4 astronomical units in mid-July to 2.85 astronomical units by late August. Exactly the behavior expected if sublimation was liberating metallic atoms trapped in or on the comet's icy matrix. The data fit a model where nickel-bearing compounds or particles embedded in the comet's structure were being released into the coma by the sublimating carbon dioxide and water, then heated by sunlight until the nickel vaporized and produced the observed emission spectrum. But this straightforward physical picture leaves the central question unanswered. Why was nickel emitting without iron for more than a month? Several theoretical explanations have been proposed, none entirely satisfactory. The first invokes nickel tetracarbonyl, a highly toxic compound with the formula NiCuRn4, where one nickel atom bonds with 4 carbon monoxide molecules. This compound is unusual because it's volatile. It can exist as a gas at relatively low temperatures, unlike most metal-bearing compounds which require extreme heat to vaporize. Nickel tetracarbonyl forms when nickel metal reacts with carbon monoxide under specific conditions, and it decomposes when heated or exposed to ultraviolet radiation, releasing pure nickel atoms and carbon monoxide. If 3I Atlas's surface contained nickel tetracarbonyl, perhaps created by space weathering reactions over millions of years of exposure to cosmic rays and interstellar carbon monoxide, then this compound could sublimate at the relatively modest temperatures the comet experienced in July, producing nickel vapor without requiring any iron to be present. The space weathering hypothesis has appeal because interstellar objects, by definition, have spent vast amounts of time exposed to the harsh radiation environment between stars. Cosmic rays, high-energy particles accelerating through the galaxy, constantly bombard any object in interstellar space, breaking chemical bonds, creating free radicals, driving unusual chemical reactions that wouldn't occur in the more sheltered environment of a planetary system. If the surface of 3I Atlas has been processed by millions of years of this bombardment, its chemistry might differ substantially from solar system comets that have spent most of their existence in the Kuiper belt or Oort cloud, regions that are still within the Sun's heliosphere and partially shielded from galactic cosmic rays. Rohan Rahatgaonkar, one of the researchers analyzing the nickel emission, suggested that chemical processes involving organic compounds on the comet's surface could create conditions favoring nickel release over iron, perhaps through differential binding to carbonaceous materials or preferential incorporation into volatile molecules. But the nickel tetracarbonyl hypothesis faces significant challenges. For one, it requires that the comet somehow accumulated substantial amounts of this exotic compound, or that nickel metal on the surface continuously generates it through reaction with the carbon monoxide in the coma. The compound is thermally unstable, decomposing at temperatures above about 180 degrees Celsius, so it couldn't survive in the warmer inner regions of any planetary system. It would need to form in the cold conditions of interstellar space or in the outer reaches of a protoplanetary disk. Moreover, iron also forms iron pentacarbonyl, FeCO5, under similar conditions, so if carbonyl formation explains the nickel vapor, we'd still expect to see iron carbonyl producing iron emission, just at potentially different rates or temperatures. The complete absence of iron in the July and early August spectra remains difficult to explain through carbonyl chemistry alone. An alternative explanation focuses on the physical separation of nickel and iron rather than chemical differences. Perhaps the nickel and iron are present in different components of the comet's structure. Nickel concentrated in volatile ices or fine dust particles that sublimate early in the heating process. Iron concentrated in refractory grains or mineral structures that require higher temperatures to vaporize. As the comet gradually heated through July and August, the nickel-rich components could have sublimated first, producing the observed nickel emission, while the iron-rich components remained frozen or solid. Only when the comet reached higher temperatures in late August would the iron-bearing materials begin to break down and release iron atoms. This scenario requires a degree of compositional heterogeneity, different materials concentrated in different regions of the nucleus or different size fractions of the dust population, but such heterogeneity is not unreasonable for an object that may have accreted in the chaotic environment of an ancient protoplanetary disk. The cyanide detections add another dimension to the chemical puzzle. Hydrogen cyanide, HCN, consists of hydrogen, carbon, and nitrogen, bonded in a linear molecule that's common in comets and represents one of the fundamental building blocks of prebiotic chemistry. The James Clerk Maxwell Telescope on Mauna Kea in Hawaii observed 3I Atlas on September 7th and detected hydrogen cyanide production at a rate of 1.5 plus or minus 0.5 times 10 to the 25th power molecules per second. A week later, on September 14th, the production rate had tripled to 4.5 plus or minus 1.9 times 10 to the 25th power molecules per second, equivalent to approximately 2 kilograms of cyanide gas per second. By September 15th, the cyanide coma had expanded to about 180,000 kilometers in diameter, roughly half the distance from Earth to the Moon, and showed clear asymmetry, elongated along the antisolar direction just like the dust tail. This asymmetry indicates that cyanide production was stronger on the day side of the nucleus and that the molecules were being swept back by solar radiation pressure along with the dust. The cyanide production rate places 3I Atlas firmly within the range of typical comets. Many solar system comets produce cyanide at similar rates when at comparable solar distances, confirming that 3I Atlas, despite its interstellar origin and unusual composition in some respects, still follows the basic template of cometary chemistry. The simultaneous increase in both cyanide and metal emission rates through August and September reflects the overall increase in activity as solar heating intensified. Everything was sublimating faster, releasing more material into the coma, creating stronger spectral signatures across multiple wavelengths. The apparent magnitude reached 14.2 on September 14th, still too faint for visual observation, but bright enough for amateur astronomers with modest telescopes to capture images showing the comet's fuzzy coma against the star fields of Libra. What remains frustrating is the lack of observations during the peak activity period at and around perihelion. The transition from nickel-only emission to nickel plus iron emission happened gradually through late August, but what happened during September and October as the comet continued to heat up? Did the nickel-to-iron ratio stabilize at some characteristic value, or did it continue to vary as different layers of the nucleus were exposed? Did new metallic species appear in the spectrum, perhaps sodium, potassium, calcium, or other elements that comets occasionally emit? These questions can't be answered until the comet emerges from solar conjunction in November and can be studied again with ground-based telescopes and spectrographs. The observations will be challenging because the comet will be dimmer after perihelion, moving away from the Sun and receiving less heating, but they're crucial for understanding the full story of this object's composition and activity. The broader question of what these metallic emissions tell us about 3I Atlas's origin remains open. The metals themselves almost certainly came from supernova nucleosynthesis, the process where massive stars forge heavy elements in their cores and then scatter those elements across the galaxy when they explode. Every atom of nickel and iron in 3I Atlas was created in the core of a star that died billions of years ago, possibly before our solar system even formed. Those atoms were incorporated into the molecular cloud that eventually collapsed to form the planetary system where 3I Atlas originated, mixed into the protoplanetary disk, accreted into planetesimals and comets. The ratios of different elements, their distribution in different minerals and molecules, all encode information about the conditions in that long-vanished system. If we can fully decode the chemical signatures in 3I Atlas, we might learn about star formation and planet formation in a part of the galaxy very different from where our Sun was born, sampling nucleosynthesis products from different stellar generations, processed by different radiation environments, incorporated into solid bodies under different temperature and pressure conditions. The metallic mystery isn't just a puzzle about nickel and iron, it's a window into the chemical diversity of planetary systems across the Milky Way. On October 21, 2025, 8 days before 3I Atlas reached perihelion, NASA made a decision that sent ripples through both scientific and conspiracy theory communities. They officially added the interstellar comet to the International Asteroid Warning Network, marking the first time an object from beyond our solar system has been included in planetary defense protocols. The IAWN, established in 2014 under the coordination of the United Nations Office for Outer Space Affairs, exists specifically to track potentially hazardous asteroids and comets that could threaten Earth. Its member organizations include space agencies, observatories, and research institutions from around the world, all sharing data and coordinating observations of near-Earth objects. The network's primary function is warning, providing early detection and trajectory predictions for anything that might pose a collision risk in the coming decades or centuries. So when 3I Atlas appeared on IAWN's tracking list, it raised immediate questions about why NASA felt compelled to apply planetary defense protocols to an object that will never come closer to Earth than 1.8 astronomical units, about 270 million kilometers, and poses absolutely no impact threat. NASA's official explanation pointed to what they termed the unpredictability of comet jets as the justification for including 3I Atlas in the IOWN training exercise scheduled to run from November 27, 2025 through January 27, 2026. Comets, unlike asteroids, are active bodies continuously ejecting gas and dust through sublimation. These jets, erupting from specific regions on the nucleus surface as sunlight heats and vaporizes ice, create rocket-like forces that can alter a comet's trajectory in ways that are difficult to predict from gravitational calculations alone. The non-gravitational accelerations caused by outgassing jets have been observed in countless solar system comets, and they're one of the primary sources of uncertainty in long-term comet orbit predictions. NASA emphasized that monitoring 3I Atlas would provide valuable training for tracking future unpredictable comets that might actually pose threats, and that the unusual nature of an interstellar object made it an ideal test case for exercising the international coordination mechanisms that IAWN was designed to facilitate. This explanation satisfied most scientists, who recognized it as a reasonable, if somewhat cautious, application of planetary defense resources. But it didn't satisfy everyone. The timing struck skeptics as suspicious. IAWN activation came precisely as 3I Atlas was entering the solar conjunction phase, the 40-day window when Earth-based observation would be impossible and the comet would be hidden behind the sun. If NASA genuinely wanted to track unpredictable jet activity, why activate the protocol just as the object became unobservable? Critics pointed to a classified military meeting that reportedly occurred on September 30th, details undisclosed, timing coincidentally aligned with 3I Atlas reaching its closest approach to Mars and entering the final month before perihelion. They noted the U.S. government experienced a partial shutdown in October, during which data processing and release from various federal agencies, including NASA, slowed or halted entirely. And most frustrating to those demanding transparency, the Mars Reconnaissance Orbiter images from the October 3rd Mars flyby, potentially the most detailed close-up observations of 3I Atlas anyone would obtain, remained unpublished weeks after being captured. The conspiracy narrative writes itself. Government discovers something unusual about the interstellar object, holds classified briefings, activates planetary defense protocols, then conveniently experiences a shutdown that delays data release during the critical observation period. Online forums exploded with speculation ranging from the plausible to the absurd. Some suggested NASA had detected trajectory changes indicating intelligent control and was quietly preparing contingency plans while maintaining public calm. Others proposed the comet was fragmenting and might spawn debris streams that could threaten satellites or even reach Earth despite the large nominal distance. The more extreme theories invoked alien signals, hidden propulsion systems, or even suggested that 3I Atlas was deploying smaller probes throughout the inner solar system during its passage, making it necessary to track not just the main object, but potentially dozens of smaller artifacts it might be releasing. The reality, as best can be determined from public information, is far more mundane but still interesting. NASA and the European Space Agency had been planning a coordinated observation campaign of 3I Atlas for months, recognizing the scientific value of studying only the third known interstellar object and the first interstellar comet that would remain observable for an extended period. The IAWN inclusion was likely a straightforward administrative decision to formalize this coordination, ensuring that observatories and space agencies worldwide shared data through established channels rather than through ad hoc arrangements. The training exercise designation simply reflects IAWN's standard operating procedures. Whenever a potentially interesting object is tracked, even if it poses no actual threat, the network uses the opportunity to practice protocols and test communication systems. The fact that no actual danger exists makes it an ideal training scenario, allowing participants to develop skills and identify system weaknesses without the pressure of responding to a genuine emergency. The spacecraft observations during perihelion, far from being secretive, were actually announced in advance and have been reported publicly as data becomes available. The GOES-19 weather satellite, operated by NOAA, captured images of 3I Atlas from October 18 through 24, showing the comet as a distinct object against the background stars with an apparent magnitude around 11 to 12. Amateur astronomer Warachate Boonplod processed the GOES-19 data and published analysis showing the comet's steady movement and gradual brightening as perihelion approached. The Solar and Heliospheric Observatory, SOHO, a joint NASA-ESA mission that monitors the Sun from the L1 Lagrange point, captured 3I Atlas in its LASCO C3 coronagraph, an instrument designed to block the Sun's disk so the faint corona can be observed. SOHO's images from late October showed the comet as it passed through the field of view, and color photometry analysis revealed something significant. The comet appeared distinctly bluer than the Sun, indicating that gas emission was contributing substantially to the visible brightness near perihelion rather than just reflected sunlight from dust. The Stereo A spacecraft, part of NASA's Solar Terrestrial Relations Observatory mission, also observed the comet using its SECI suite of instruments, specifically the HI-1 heliospheric imager and the COR-2 coronagraph. Stereo A orbits the Sun ahead of Earth, providing a different viewing angle than Earth-based or L1-based instruments, and its observations in September and October captured 3I Atlas approaching perihelion from a unique perspective. Analysis of the Stereo A photometry showed the comet was brightening rapidly, following a power law where brightness scaled with heliocentric distance raised to the negative 7.5 power, plus or minus 1.0. This steep brightness increase, much faster than the typical inverse square relationship expected for reflected sunlight, confirmed that activity was accelerating dramatically as solar heating intensified. The comet wasn't just getting closer and therefore appearing brighter due to geometry, it was actually producing more gas and dust at an exponentially increasing rate. Most impressive were the observations by GOES 19's CCOR-1 coronagraph, a relatively new instrument that managed to resolve 3I Atlas as an extended source rather than just a point of light. The images showed a coma approximately 4 arc minutes in diameter, equivalent to about 60,000 to 80,000 kilometers at the comet's distance, confirming the presence of a substantial atmosphere around the nucleus. This extended coma is exactly what you'd expect from a comet experiencing vigorous sublimation at perihelion, not what you'd see from an inert spacecraft or asteroid. The combination of the extended coma, the blue color indicating gas emission, and the steep, brightening curve all point unambiguously toward natural cometary activity peaking at perihelion just as predicted by standard models. The ExoMars Trace Gas Orbiter and Mars Express observations from October 1st through 7, when 3I Atlas was near Mars, have been published and show the comet displaying typical cometary features: a clear coma, appropriate brightness for the distance and activity level, spectral characteristics consistent with dust and gas. The Mars Reconnaissance Orbiter observations, while not yet released in detail, have no particular reason to show anything different. The delay in publication most likely reflects the government shutdown's impact on data processing pipelines rather than any deliberate suppression. Scientific data from NASA missions typically require weeks to months between acquisition and public release, allowing time for calibration, analysis, and preparation of properly formatted datasets. The October shutdown added delays to already slow processes, frustrating both the public and researchers waiting for the data. The Europa Clipper and Hera spacecraft, both recently launched and en route to their primary mission destinations, were positioned to potentially encounter 3I Atlas's ion tail during the perihelion period from October 25th through November 1st. The ion tail, formed by ionized gas molecules swept back by the solar wind's magnetic field, can extend millions of kilometers from the nucleus and form a thin but detectable structure that spacecraft instruments can sample. If either Clipper or Hera happened to cross through the tail, their instruments would detect anomalous ion concentrations and characteristic chemical signatures. The JUICE spacecraft, ESA's Jupiter Icy Moons Explorer, passed 0.428 astronomical units from 3I Atlas on November 4th and was scheduled to observe the comet with its cameras and spectrometers. However, thermal conditions in the spacecraft meant that data wouldn't be transmitted back to Earth until February 2026 at the earliest, a delay built into the mission plan and having nothing to do with any desire to suppress findings. Looking ahead, the Juno spacecraft orbiting Jupiter represents the final opportunity for close spacecraft observations when 3I Atlas passes 0.36 astronomical units from Jupiter on March 16, 2026. Juno's instruments, designed to study Jupiter's magnetosphere, atmosphere, and interior, could potentially observe the comet as it makes this distant flyby. However, Juno is low on fuel and experiencing engine issues after years of operation in Jupiter's harsh radiation environment, so whether it can spare resources for comet observations remains uncertain. The Psyche mission, en route to study a metallic asteroid, passed 0.312 astronomical units from 3I Atlas on September 4th, but did not conduct observations, presumably because the spacecraft's instruments were not properly configured, or the science team chose not to divert from primary mission objectives. The IAWN activation, viewed in context, appears to be less about planetary defense and more about international scientific coordination. Including 3i Atlas in the network ensured that observatories worldwide would share data promptly, that trajectory predictions would be updated consistently as new observations came in, and that any unexpected developments, such as fragmentation or unusual non-gravitational accelerations, would be detected and communicated quickly. The no immediate threat language in NASA's announcement wasn't a coded warning, it was a straightforward statement of fact. This object poses no danger to Earth, and including it in IAWN is about training and scientific coordination rather than threat mitigation. But the timing and circumstances created perfect conditions for speculation, and in the absence of complete transparency, speculation inevitably fills the vacuum. What actually happened at perihelion, what changes occurred to the comet during those 40 dark days when no Earth-based telescope could observe, will become clear only when 3i Atlas emerges from behind the Sun in mid-November and can be studied again by the global network of observatories that have been tracking it since July. When Harvard astronomer Avi Loeb published his analysis of 3i Atlas on the preprint server arXiv on July 16, 2025, he knew exactly what kind of reaction he would provoke. The paper, titled "Is the Interstellar Object 3i Atlas Alien Technology?" laid out a series of observations that Loeb argued made this comet worthy of extraordinary scrutiny and suggested that the possibility of artificial origin, while not proven, deserved serious consideration rather than immediate dismissal. He calculated that there was approximately a 30 to 40% chance that 3i Atlas represented technology from another civilization, a statement that would dominate headlines for months and draw fierce criticism from his colleagues who saw the estimate as wildly speculative and damaging to legitimate scientific discourse. But Loeb has never been one to shy away from controversy, and his willingness to publicly entertain the extraterrestrial hypothesis, regardless of professional cost, has made him both a hero to those frustrated with scientific conservatism and a pariah to those who believe such speculation undermines the careful, methodical work of astronomy. Loeb's arguments in the July paper centered on several features he considered improbable for a natural object. First, the apparently large size. Early estimates based on the comet's brightness suggested a nucleus diameter of approximately 46 kilometers, substantially larger than most known comets, and comparable to the biggest objects in the Kuiper Belt. Such a large interstellar object would be rare, requiring massive gravitational perturbations to eject it from its birth system, and Loeb questioned whether the ejection mechanisms we understand could produce objects of this scale traveling at 3i Atlas's high velocity. Second, the trajectory alignment with the ecliptic, tilted just 5 degrees from the plane containing all the planets, struck Loeb as statistically unusual for a randomly approaching interstellar visitor. Third, at the time of his July paper, spectroscopic observations had not yet identified many specific chemicals in the comet's coma, and Loeb noted this apparent lack of identifiable cometary molecules as potentially significant, though he acknowledged this might simply reflect the comet's distance and the difficulty of observations. The scientific response was swift and unforgiving. Chris Lintott, the Oxford astronomer and BBC presenter, expressed disappointment with Loeb's paper in multiple interviews, arguing that it distracted attention from the genuine scientific work being conducted by dozens of research teams studying 3i Atlas. Lintott emphasized that by the time Loeb's paper appeared, numerous telescopic observations demonstrating classical cometary activity had already been made, including detections of a clear coma, evidence of sublimation, and behavior entirely consistent with a natural comet. He noted that the overwhelming consensus among comet researchers was that 3i Atlas is indeed a comet, not a spacecraft, and that Loeb's speculation, while not technically impossible, lacked the evidentiary support needed to justify the attention it was receiving. The fact that media outlets gave more coverage to Loeb's controversial hypothesis than to the careful observational work of astronomers actually studying the comet's composition and activity frustrated the broader community. Darrell Seligman, a planetary scientist who has published extensively on interstellar objects, provided a detailed technical response to Loeb's arguments. Seligman pointed out that the chemicals Loeb claimed were not detectable had simply not been observed yet because the comet was still too far from the Sun for many volatile species to sublimate vigorously enough to produce strong spectral signatures. He noted that within weeks of Loeb's paper, the James Webb Space Telescope had confirmed carbon dioxide, water, and carbon monoxide in the coma, with the Swift Observatory detecting water vapor and hydroxyl radicals shortly thereafter. All of these detections confirmed that 3I Atlas was outgassing exactly as expected for a natural comet, producing the standard suite of cometary molecules that decades of comet research have documented. Seligman argued that Loeb's paper had jumped to conclusions based on incomplete data, speculating about an absence of chemicals that subsequent observations quickly revealed were present all along. The size estimate also crumbled under scrutiny. Hubble Space Telescope observations on July 21st, just 5 days after Loeb's paper appeared, provided much better constraints on the nucleus diameter, estimating it at between 0.32 and 5.6 kilometers, with the most likely value less than 1 kilometer. This placed 3I Atlas firmly in the range of typical comet nuclei, comparable to 2I Borisov, which had a nucleus approximately 0.5 kilometers across. The earlier estimates of 46 kilometers had been based on the comet's total brightness, which includes the contribution from the coma, the vast cloud of gas and dust surrounding the nucleus. When you observe a comet from a distance, you see the integrated light from both the nucleus and coma, and that the coma can be thousands to hundreds of thousands of kilometers in diameter, making the comet appear much larger than the solid nucleus actually is. Hubble's high-resolution and careful photometric analysis allowed astronomers to separate the nucleus contribution from the coma contribution, revealing that the solid object at the center was actually quite small, not the massive body Loeb had imagined. But Loeb wasn't alone in his speculation. Michio Kaku, the theoretical physicist and popular science communicator, made even bolder statements in late October as perihelion approached. In interviews aired on October 26 and 27, just days before the critical event, Kaku told reporters that the world will know if there are aliens in 3 days, referring to the October 29th perihelion date. He described the perihelion passage as Judgment Day, the moment when 3I Atlas would either reveal itself as a natural comet through predictable behavior or demonstrate artificial characteristics through anomalous activity or trajectory changes. Kaku specifically highlighted the Oberth maneuver possibility, explaining to a general audience how a spacecraft could use perihelion as the optimal point to change its velocity or trajectory, taking advantage of already being at maximum speed to amplify any additional thrust. Kaku's media appearances generated enormous public interest, but also drew criticism from astronomers who felt he was hyping unlikely scenarios without adequately explaining the overwhelming evidence for natural origin. His suggestion that people take vacation before October 29th, who knows what will happen, struck many as irresponsible fear-mongering, potentially causing unnecessary anxiety among people unfamiliar with the actual science. But Kaku defended his statements, arguing that even if the probability of artificial origin was low, the implications would be so profound that the possibility merited serious attention and public discussion. He framed the perihelion observations as a critical test. If the comet's trajectory after perihelion differed from predictions based purely on gravitational dynamics and reasonable outgassing forces, that would constitute compelling evidence of intelligent control and should prompt a major reassessment of what 3I Atlas actually is. The Oberth maneuver concept became central to both Loeb's and Kaku's arguments. In orbital mechanics, the Oberth effect describes how a spacecraft can gain more energy by burning its engines when moving at high velocity through a deep gravitational well compared to burning the same amount of fuel in weaker gravity or at lower speed. The mathematics are straightforward. Kinetic energy scales with velocity squared, so adding a given amount of velocity when you're already moving fast produces more total energy than adding the same velocity change when moving slowly. For 3I Atlas, perihelion represents the moment of maximum velocity, 68 kilometers per second, and the deepest point in the Sun's gravitational well along its trajectory. If an intelligent civilization wanted to maximize the efficiency of changing this object's trajectory or increasing its speed, they would wait for precisely this moment to activate propulsion systems. The fact that perihelion occurred during solar conjunction, when Earth-based observation was impossible, only added to the appeal of this scenario for those inclined to suspect artificial control. Loeb also raised the possibility of self-luminosity, suggesting that if 3I Atlas were generating its own light from power systems or engines rather than merely reflecting sunlight, this would be a clear indicator of technology. He pointed to the comet's brightness variations and the difficulty in modeling its light curve as potential evidence that internal light sources might be contributing to observations. But this claim fell apart under careful analysis. Comets are absolutely capable of emitting their own light through gas fluorescence, where ultraviolet radiation from the sun excites gas molecules in the coma, which then emit visible light at specific wavelengths. This process is well understood and routinely observed in comets. The spectroscopic observations of 3I Atlas clearly showed emission lines from cyanide, carbon dioxide, and other molecules, proving that gas fluorescence was indeed occurring. There's no need to invoke artificial light sources to explain the comet's brightness, and no evidence that such sources exist. The public discourse around 3I Atlas became a case study in how scientific uncertainty gets communicated and misinterpreted. Within the professional astronomical community, the consensus was clear and strong. This is a natural comet displaying typical cometary behavior, and while it has some unusual characteristics such as high carbon dioxide abundance and fast velocity, these features fall within the range of natural variation and don't require exotic explanations. The probability that 3I Atlas represents alien technology was, in the estimation of most experts, vanishingly small, well below 1%, and perhaps below 0.1%. But Loeb's 30 to 40% estimate, delivered with the authority of a Harvard professor, reached far larger audiences through mainstream media coverage than the careful spectroscopic papers and photometric analyses published by comet specialists. The public ended up with a deeply skewed perception of scientific opinion, believing the question was open and actively debated, when in fact the debate was largely one-sided. Scott Manley and David Kipping, both with substantial online followings and reputations for careful analysis, produced content specifically addressing and refuting Loeb's statistical arguments. Manley's video demonstrated where Loeb's probability calculations had gone wrong, showing that the ecliptic alignment, while interesting, wasn't as improbable as claimed once you properly accounted for observational bias and the three-dimensional geometry of the comet's approach. Kipping's analysis focused on the multiple testing problem. When you look at dozens of characteristics of an object, you're bound to find a few that seem unusual just by chance, and you can't simply cherry-pick the most anomalous features and claim they prove something extraordinary. Both emphasized that the totality of evidence, including the spectroscopic detections, the coma morphology, the dust production rates, and the temporal evolution of brightness, all pointed unambiguously toward a natural comet. Yet the speculation persisted, fueled by the tantalizing mystery of what happened during perihelion. Loeb framed October 29th as an acid test, a day when the comet's true nature would be revealed through how it responded to intense solar heating and whether it exhibited any signs of maneuverability. He noted that a natural comet, held together by weak gravitational forces and the cohesion of ice, might fragment under the stress of 770 watts per square meter of heating at perihelion, breaking into smaller pieces that would sublime more rapidly and create a dramatic brightening. An artificial spacecraft, constructed from metals and engineered materials, would survive the heating intact and might take advantage of the optimal geometry to perform course corrections. If 3I Atlas deployed smaller probes, if it exhibited artificial lighting that couldn't be explained by reflected sunlight or gas fluorescence, if it showed excess heat that might indicate engines operating, these would all serve as indicators of technology. None of these extraordinary signatures has been definitively observed. The spacecraft that monitored 3I Atlas during perihelion, including GOES-19, SOHO, and the Mars orbiters, all reported observations consistent with a brightening comet displaying vigorous outgassing, exactly as expected. The GOES 19 coronagraph resolved an extended coma approximately 60,000 to 80,000 kilometers in diameter, and color photometry showed the comet appeared distinctly bluer than the Sun, indicating that gas emission from excited molecules was contributing substantially to the visible brightness. These observations confirm natural cometary activity, not spacecraft operations. The rapid brightening observed in the final days before perihelion, following a steep power law with heliocentric distance, matches models of accelerating sublimation as temperatures rise, not the steady light output you'd expect from artificial illumination. The final verdict on whether the trajectory changed during perihelion will come in November and December, when Earth-based telescopes can observe 3I Atlas again and precisely measure its position and velocity. If the comet's path matches predictions based solely on gravitational forces plus reasonable estimates of outgassing-induced accelerations, that will close the door on the artificial control hypothesis. If the trajectory shows deviations that can't be explained by natural processes, that will reopen questions and demand more careful investigation. As of now, with perihelion having occurred yesterday on October 29th at 11:47 Universal Time, we're in the waiting period, the days and weeks when the comet remains hidden behind the Sun and its secrets remain locked away. Loeb's 30 to 40% probability will be tested against reality, and Kaku's prediction that October 30th will determine if it's rock or alien technology will prove either prophetic or premature, most likely the latter given everything we know about comets and the evidence already in hand. When the James Webb Space Telescope turned its infrared spectrograph toward 3I Atlas on August 6, 2025, astronomers expected to find water vapor, the dominant volatile in nearly every comet ever observed. What they found instead rewrote the textbook on what an interstellar comet can be. The spectrum revealed carbon dioxide production at 129 kilograms per second, an impressive outgassing rate for any comet at that distance from the Sun. But the water production measured only 6.6 kilograms per second, yielding a carbon dioxide to water ratio of approximately 8:1. This composition is so unusual, so far outside the normal range for solar system comets, that it demands a complete rethinking of where 3I Atlas formed and what conditions shaped its chemistry billions of years ago. Only one other comet has ever shown a comparable carbon dioxide dominance, C2016 R2 Pan-STARRS, a bizarre object discovered in our own solar system that challenged every assumption about cometary composition. To understand why this matters, you need to grasp what comets typically are. The classical model describes them as dirty snowballs, mixtures of water ice and rocky dust particles bound together by weak gravity and the cohesive strength of the ice itself. Water dominates the composition because water is abundant throughout the universe, formed from hydrogen and oxygen, the first and third most common elements respectively. When protoplanetary disks cool below about 150 Kelvin, water ice condenses out of the gas and becomes available to incorporate into solid bodies. In the outer regions where comets form, beyond the snow line where water remains frozen, this ice becomes the primary building material. Other volatile ices mix in: carbon dioxide, carbon monoxide, methane, ammonia, all important but secondary to water. Typical solar system comets show water production rates 10 to 100 times higher than carbon dioxide production, sometimes even more extreme. That's why detecting water vapor has historically been the gold standard for confirming that an object is genuinely a comet rather than a rocky asteroid. 3I Atlas inverts this relationship completely. For every kilogram of water vapor released, 8 kilograms of carbon dioxide sublimate, creating a coma that's fundamentally different from what we normally see. This immediately tells us that the comet formed in an environment where carbon dioxide was more available than water, or where water was somehow depleted relative to carbon dioxide. Carbon dioxide ice forms at higher temperatures than water ice under typical pressure conditions, about 195 Kelvin compared to 273 Kelvin at Earth atmospheric pressure, though these numbers change in the near vacuum of space. But carbon dioxide is also chemically simpler, just one carbon atom bonded to two oxygen atoms, while water requires hydrogen, and hydrogen is prone to escaping from warm environments or being locked into other chemical forms. In certain regions of protoplanetary disks, particularly those around low metallicity stars where oxygen is abundant but carbon chemistry differs from solar composition, you might create conditions favoring carbon dioxide over water ice. The JWST observations also detected carbon monoxide at 14 kilograms per second, giving a carbon monoxide to water ratio of 1.4 to 1, which is high but less dramatically unusual than the carbon dioxide number. Carbon monoxide is the most volatile of the three major cometary ices, remaining frozen only at temperatures below about 70 Kelvin, well below the sublimation points of carbon dioxide or water. The fact that 3I Atlas is releasing substantial carbon monoxide at 3.32 astronomical units, where JWST observed it, indicates that this ultra-volatile ice is distributed through the comet's structure, not just concentrated in a deep, frozen core. As the outer layers sublime away, fresh carbon monoxide-rich material becomes exposed and immediately begins outgassing. The carbonyl sulfide detection at 0.43 kilograms per second adds sulfur to the chemical inventory and suggests complex organic chemistry occurred in the comet's formation environment, producing molecules more sophisticated than simple ices. The detection of carbon-13, the heavier stable isotope of carbon in the form of 13CO2 emission lines, potentially offers a window into nucleosynthesis in the comet's birth system. The ratio of carbon-13 to carbon-12 varies slightly depending on where and when the carbon was formed, with different stellar generations and different regions of the galaxy producing subtly different isotopic signatures. Unfortunately, dust obscuration in the coma made it difficult to precisely quantify the 13C-12C ratio from the JWST spectrum, but even confirming the presence of the heavy isotope provides valuable data that future higher-resolution observations might refine into an accurate measurement. If we could determine that 3I Atlas has an unusual carbon isotope ratio compared to solar system comets, that would directly confirm it formed from material processed through different stellar nucleosynthesis cycles in a different part of the galaxy with different chemical enrichment history. The Swift Observatory observations from July 31st and August 1st revealed another fascinating detail about the water component. It wasn't sublimating directly from the nucleus. The data suggested that water ice grains were being lifted off the surface by the outgassing carbon dioxide, carried 4,000 to 10,000 kilometers into the coma before finally warming up enough to sublime. This mechanism completely changes how we think about water release from this comet. Instead of water ice on the surface absorbing sunlight and turning to vapor, the water exists as particles embedded in or mixed with the carbon dioxide, and it's the CO2 sublimation that drives the activity, ejecting everything into space. Only after traveling thousands of kilometers, tumbling through space while absorbing solar radiation, do these tiny ice grains finally reach the temperature where water begins to sublime. The hydroxyl radicals that Swift detected are the breakdown products of that water vapor, created when ultraviolet photons from the sun split water molecules into hydrogen and OH. This explains why 3I Atlas was active so early, at 6.4 astronomical units when TESS first observed it in May, much farther than the 3 to 4 astronomical units where water-dominated comets typically become active. Carbon dioxide doesn't wait for close approaches to the sun. It starts sublimating as soon as surface temperatures exceed about 80 to 100 Kelvin, which occurs well beyond Jupiter's orbit depending on the surface properties and albedo. The early activity that allowed pre-discovery detection, the five-fold brightness increase that NASA couldn't initially explain, all make sense once you understand that carbon dioxide was driving the show from the very beginning. As 3I Atlas fell deeper into the sun's gravity well through summer 2025, the carbon dioxide sublimation rate accelerated exponentially, releasing more gas, lifting more dust, creating a larger and brighter coma week by week. The SphereX observations in mid-August confirmed the JWST findings, measuring the carbon dioxide coma extending to a radius of 348,000 kilometers, a bubble of gas nearly as large as the distance from Earth to the Moon. SphereX, optimized for infrared observations, could track the carbon dioxide distribution across this enormous volume, mapping how the gas density decreased with distance from the nucleus. But SphereX lacked the sensitivity to detect water vapor or carbon monoxide, so it provided confirmation of the carbon dioxide dominance without adding new constraints on the other species. The sheer size of the CO2 coma reflects both the high production rate and the long lifetime of carbon dioxide molecules in space before solar ultraviolet dissociates them into carbon monoxide and atomic oxygen. Two competing hypotheses attempt to explain why 3I Atlas is so enriched in carbon dioxide relative to water. Hypothesis A proposes that the nucleus is genuinely carbon dioxide rich, formed in a region of its protoplanetary disk close to the CO2 frost line, where carbon dioxide could condense, but conditions were too warm or chemically unsuitable for water ice to dominate. This scenario requires a parent star with properties different from our Sun, perhaps a low metallicity star from the thick disk of the Milky Way, where element abundances differ from the solar neighborhood. Such a star would have a protoplanetary disk with different chemistry, potentially favoring carbon oxides over water in the planet-forming regions. The comet would have spent billions of years exposed to galactic cosmic rays and interstellar radiation, gradually processing its surface and perhaps further depleting any water ice through radiolysis, the breaking of chemical bonds by high-energy particles. Hypothesis B takes a different approach, suggesting that 3I Atlas might actually have a water-rich nucleus hidden beneath a thick insulating crust. Comets can develop crusts over time as the most volatile materials sublime away from the surface, leaving behind dust and less volatile ices that form a protective layer. If this crust is thick and carbon dioxide rich, it would preferentially release CO2 when heated, while the water ice underneath remains trapped and unable to sublime efficiently. The ice particles ejected by the carbon dioxide jets could include these deeper water-rich materials, explaining why some water is detected but at such low rates compared to the CO2. This hypothesis predicts that as 3I Atlas becomes more active, as the surface layers sublime away and fresh material becomes exposed, the water-to-carbon dioxide ratio should increase. Future JWST observations scheduled for December, after perihelion, when the comet should be highly active and potentially has shed its outer layers, will test this prediction. The Very Large Telescope, Nordic Optical Telescope, and Röschen Observatory polarimetry observations provide indirect evidence about the dust composition. The negative polarization at small phase angles that they measured suggests the coma contains both icy particles and dark organic material, specifically tholins, the complex carbon-rich compounds that form when simple organics are irradiated. Tholins are reddish-brown in color and have been found on Pluto, Titan, Triton, and many trans-Neptunian objects, surfaces that have been exposed to radiation over billions of years. Their presence in 3I Atlas's coma indicates that the comet's surface has been significantly processed during its long interstellar journey. The combination of ice and dark organics creates the polarization signature that was observed and also suggests that the comet might have lower albedo, lower reflectivity than pristine icy bodies, which would affect how efficiently it absorbs solar heating. The near-total absence of carbon chain molecules adds another puzzle to the compositional story. The MDM Observatory and Very Large Telescope specifically searched for C2 and C3, the dicarbon and tricarbon molecules that are common in many comets and thought to be fragments of larger organic compounds broken apart by solar ultraviolet. Neither was detected, making 3I Atlas one of the most carbon chain-depleted comets on record. This depletion might reflect the comet's formation environment. Perhaps it formed from material that lacked the complex organics that produce carbon chains when photodissociated. Alternatively, the long exposure to cosmic rays in interstellar space might have destroyed these compounds, breaking them down into simpler molecules or altering their chemical structure so they no longer produce the expected spectral signatures. The presence of cyanide and carbonyl sulfide shows that some complex chemistry did occur, but apparently not the kind that produces abundant carbon chains. Hubble Space Telescope observations planned for November will use ultraviolet spectroscopy to measure sulfur to oxygen ratios and monitor the outbound gas composition as 3I Atlas recedes from the Sun. Sulfur chemistry provides clues about oxidation states and chemical processing in the protoplanetary disk where the comet formed. The sulfur to oxygen ratio in particular can be compared to measurements from other comets and to theoretical predictions for different formation scenarios. If 3I Atlas shows unusual sulfur abundance or unusual ratios of different sulfur-bearing species, that would add weight to the hypothesis that it formed in a chemically distinct environment. The ultraviolet wavelengths Hubble will observe are blocked by Earth's atmosphere, so ground-based telescopes can't make these measurements, making Hubble's contribution uniquely valuable despite its smaller aperture compared to ground-based giants. The December JWST observations represent the critical test. By that time, 3I Atlas will have passed perihelion, experienced maximum heating, and potentially shed surface layers that might have been hiding water-rich material underneath. If the carbon dioxide to water ratio drops significantly, approaching values closer to typical comets, that would support Hypothesis B, the thick crust model. If the ratio remains stubbornly high at 8:1 or similar, that would favor Hypothesis A, genuine carbon dioxide enrichment in the nucleus composition. JWST's infrared spectrograph can measure these production rates with high precision, potentially detecting changes in the ratio of just a factor of 2 or 3, enough to discriminate between the competing hypotheses. The observations will also track how the total outgassing rate evolves, whether the comet becomes less active as it moves away from the Sun following predictable sublimation physics, or whether it shows unexpected behavior that might indicate structural changes like fragmentation or large-scale ice avalanches exposing fresh material. The broader question this compositional mystery raises is how common are carbon dioxide-rich comets in the galaxy? Is 3I Atlas an extreme outlier, a one-in-a-million object that formed under exceptionally unusual circumstances, or does it represent a population of comets that formed around stars very different from our Sun? The discovery of C-2016 R2 Pan stars in our own solar system, showing similarly high CO2, suggests that such objects aren't impossibly rare. Perhaps they form in the outer regions of protoplanetary disks where carbon monoxide ice is abundant, and chemical reactions convert some of that CO into CO2 through radiolysis or other processes. Perhaps they represent material from the early galaxy, incorporated into planetary systems when metallicity was lower and chemical pathways different. Or perhaps there are multiple formation routes to creating carbon dioxide-rich comets, and 3I Atlas simply took one of those less traveled paths. Every measurement of its composition brings us closer to answering these questions and understanding the chemical diversity of planetary systems beyond our own. The calendar now holds a date that might answer the question that has captivated scientists and conspiracy theorists alike for the past 4 months. December 19, 2025, when 3I Atlas makes its closest approach to Earth at 1.8 astronomical units, approximately 270 million kilometers, represents the final opportunity for ground-based telescopes to observe this interstellar visitor with optimal geometry before it recedes into the outer solar system and eventually departs forever. But the real revelation won't come from the Earth flyby itself, which is actually quite distant, farther than the Sun's distance from us. The revelation will come in the weeks leading up to that date, starting in mid-November, when the comet emerges from behind the Sun and becomes observable again from Earth. Those first observations, comparing the comet's actual position and velocity to predictions made months earlier, will definitively answer whether anything extraordinary happened during the 40 dark days around perihelion, whether the trajectory changed in ways that natural processes cannot explain, whether Avi Loeb's controversial hypothesis holds any validity or collapses under the weight of evidence. The timeline of what comes next is precisely mapped. 3I Atlas passed perihelion on October 29th at 11:15 Universal Time, racing around the Sun at 68 kilometers per second at a distance of 1.36 astronomical units, hidden from Earth behind 865,000 miles of solar plasma. 5 days later, on November 3rd, it passes Venus at 0.65 astronomical units, still too close to the Sun in angular terms for Earth-based observation, but moving steadily away from solar conjunction. By November 9th, the comet finally achieves more than 30 degrees of angular separation from the Sun, clearing the threshold where it can be safely observed just before sunrise, low in the eastern sky as dawn approaches. Amateur astronomers with telescopes of at least 8 inches aperture will have their first chance to photograph the comet since early October, capturing its position against the background stars, measuring how bright it appears, documenting the size and shape of its coma and tail. Those initial November observations carry enormous weight. Astronomers have precise predictions for where 3I Atlas should be at every moment, calculated from the trajectory established through hundreds of observations from July through early October. These predictions account for the Sun's gravity pulling the comet along its hyperbolic path, adjusting the velocity and direction according to Newtonian mechanics with Einstein's general relativity corrections applied. They also include reasonable estimates for non-gravitational forces, the rocket effect from asymmetric outgassing jets pushing the nucleus in unpredictable directions, based on models of how comets typically behave. If the November observations show the comet exactly where predicted, within the error bars that account for outgassing uncertainty, then the trajectory is natural, the comet is natural, and the alien spacecraft hypothesis dies definitively. If the observations show significant deviations, velocity changes that exceed what cometary jets can plausibly produce, trajectory alterations that suggest deliberate maneuvering, then everything changes, and the scientific community will face the most profound discovery in human history. Michio Kaku's prediction that October 30th will determine if it's rock or alien technology was premature, as most astronomers expected. The determination doesn't come on a single day, it comes gradually as data accumulates through November and December, as multiple independent observations confirm or refute the trajectory predictions, as the statistical confidence grows that we're either seeing natural behavior or something genuinely anomalous. Kaku's emphasis on the Oberth maneuver remains relevant. If an intelligent civilization controlling 3I Atlas wanted to change its trajectory efficiently, perihelion on October 29th was the optimal moment, when the comet was moving fastest, and any velocity change would be amplified by the Sun's deep gravitational well. But detecting such a maneuver requires patience, requires careful astrometry, measuring the comet's position to within arcseconds, requires comparing those positions to predictions and calculating whether the residuals, the differences between observation and theory, are larger than natural processes can explain. Throughout December, as 3I Atlas moves through the constellations Virgo and Leo in the northern hemisphere sky, it will gradually dim as it recedes from the Sun and receives less heating, driving lower sublimation rates and smaller coma production. The apparent magnitude is expected to drop below 12 by mid-December, making it accessible only to serious amateur astronomers with good telescopes and dark skies, but still bright enough for professional observatories to track with ease. The December 19th closest approach to Earth, while not particularly close in absolute terms, provides optimal viewing geometry where the comet's angular size reaches maximum and any details in the coma structure or tail morphology become easiest to resolve. Professional observatories will dedicate time to spectroscopy, measuring the production rates of carbon dioxide, water, cyanide, and other molecules to see how they've evolved since the August observations, testing whether the chemical composition has changed as deeper layers of the nucleus become exposed. The Hubble Space Telescope observations scheduled for November represent one of the most anticipated datasets. Hubble's ultraviolet spectrograph will measure sulfur to oxygen ratios and look for molecules that can only be detected in wavelengths blocked by Earth's atmosphere. These observations will monitor the outbound activity, tracking how the comet's behavior changes as it moves away from perihelion and solar heating decreases. If the comet fragments, if it shows unexpected brightening or fading, if it develops new jets or changes its spin rate, Hubble will detect these changes and provide data that ground-based telescopes cannot. The James Webb Space Telescope observations in December will revisit the carbon dioxide to water ratio question, potentially resolving whether the extreme 8-to-1 ratio persists or whether water production has increased as predicted by the thick crust hypothesis. The spacecraft observations add critical perspectives that Earth-based telescopes cannot provide. The Jupiter Icy Moons Explorer, JUICE, passed within 0.428 astronomical units of 3I Atlas on November 4th and attempted observations with its cameras, spectrometers, and particle sensors. However, thermal constraints during JUICE's passage through the inner solar system mean that data won't be transmitted to Earth until February 2026 at the earliest, a frustrating delay, but one built into the mission design to protect the spacecraft's electronics and instruments. When that data finally arrives, it will provide a completely different viewing angle than Earth had, potentially revealing asymmetries in the coma or tail that weren't visible from our perspective. The Europa Clipper and Hera spacecraft may have encountered 3I Atlas's ion tail between October 25 and November 6, potentially detecting characteristic changes in the solar wind and magnetic field structures associated with the comet's interaction with the Sun's plasma environment. The ultimate spacecraft observation comes on March 16, 2026, when 3I Atlas passes just 0.36 astronomical units, about 54 million kilometers, from Jupiter. This is close enough that Jupiter's enormous gravity will measurably deflect the comet's trajectory, adding or subtracting velocity depending on the exact geometry of the flyby, potentially changing the outbound path in ways that careful orbital calculations can predict. The Juno spacecraft, having orbited Jupiter since 2016, might be able to observe the flyby if mission controllers can spare the fuel and attitude control resources needed to point its instruments at the comet. But Juno is aging, low on fuel, experiencing engine problems after years in Jupiter's brutal radiation environment, so whether it can contribute remains uncertain. If Juno observations happen, they'll provide the last close-up look at 3I Atlas before it disappears into the outer solar system, accelerating back toward interstellar space at 58 kilometers per second, never to return. The rotation period measurements offer another test of the comet's nature. Multiple observatories measured the rotation at approximately 16 hours, with slight variations between different observation sets suggesting either measurement uncertainties or genuine changes in the spin rate over time. Brightness variations decreased from 0.3 magnitudes in July to 0.2 magnitudes later in the summer, likely because increasing coma activity obscured the nucleus and smoothed out the brightness fluctuations that occur when an irregularly shaped object rotates. If the comet is natural, the rotation should follow predictable patterns, perhaps slowing down or speeding up slightly due to torques from asymmetric outgassing jets, but remaining broadly consistent. If the rotation shows sudden changes, starts and stops that don't correlate with outgassing activity, that could indicate attitude control systems adjusting the object's orientation, though such changes would need to be dramatic and unambiguous to be convincing. The cultural impact of 3I Atlas extends beyond science into prophecy and speculation. Online commentators have linked the comet's appearance to predictions attributed to Nostradamus and Baba Vanga, both of whom supposedly foresaw significant events or revelations in 2025. These connections are almost certainly retrofitted interpretations, vague prophecies that can be mapped onto any unusual event, but they've contributed to the public fascination with this object. The debate among physicists and astronomers about 3I Atlas has been unusually public and contentious, playing out in preprint servers, social media, and news interviews rather than being confined to academic journals and conference presentations. This transparency has benefits, allowing the public to see how science actually works with disagreement and debate, but it also creates confusion when non-specialists can't distinguish between mainstream consensus and fringe speculation. A scientific mission to intercept 3I Atlas was never feasible given the timeline and available technology. A study by Atsuhiro Yaganuma, published in July 2025, calculated that launching a spacecraft from Earth to rendezvous with the comet would require a delta V, a change in velocity, of at least 24 kilometers per second, well beyond the capabilities of current propulsion systems and launch vehicles. Even the most powerful rockets with the most efficient trajectories couldn't deliver a meaningful payload to 3I Atlas before it passes through and departs. Interestingly, the study found that launching from Mars would require only about 5 kilometers per second of delta V, making a Mars-launched interception mission theoretically feasible with technologies that exist or are in development. But no such Mars infrastructure exists, no launch facilities on the Martian surface, no spacecraft waiting in Mars orbit with the fuel and equipment needed for such a mission. Humanity missed its chance, learning of 3I Atlas too late to mount an interception, forced to observe from a distance rather than sample directly. The long-term fate of 3I Atlas is already written. After the Jupiter flyby in March 2026, the comet will continue outward, its velocity gradually decreasing as the Sun's gravity pulls it back, but never decreasing enough to capture it. The hyperbolic orbit with eccentricity 6.137 guarantees that 3I Atlas will escape the solar system, crossing back through the heliopause sometime in the 2030s or 2040s, re-entering the interstellar medium from which it came. Its velocity will asymptotically approach 58 kilometers per second, the same speed it arrived with, carrying it toward whatever stellar neighborhood lies in that direction. At 58 kilometers per second, 3I Atlas will take roughly 70,000 years to travel 1 light-year, meaning it will take millions of years to reach another star system, billions of years to cross significant fractions of the galactic disk. If it is a natural comet, it will eventually sublime away completely, losing all its volatile ices through exposure to cosmic rays and rare encounters with interstellar clouds, leaving behind only a dead rocky core that will drift through the galaxy indefinitely, a frozen relic of a planetary system that died long ago. But if Loeb is right, if the 30 to 40% probability he assigned to artificial origin somehow holds, then 3I Atlas will continue its mission, whatever that mission might be, exploring other star systems, gathering data on planetary architectures and stellar properties, perhaps eventually returning to whatever civilization sent it, or perhaps operating autonomously for millions or billions of years without ever reporting home. The December observations will test this hypothesis as rigorously as observations can. A natural trajectory, natural activity patterns, natural composition, all consistent with a comet ejected from another planetary system billions of years ago and wandering through the galaxy ever since, will close the book on speculation. An anomalous trajectory, unexplained velocity changes, behavior that violates physical models of cometary activity, will open that book to entirely new chapters and force humanity to confront the possibility that we've been visited by technology from another world. The amateur astronomy community has already mobilized for the November and December observations. Forums and observing networks are coordinating efforts to photograph 3I Atlas from multiple locations, ensuring redundancy and eliminating the possibility that any unusual findings represent local artifacts or individual observer errors. This distributed observing campaign guarantees transparency, making it impossible for any single institution to suppress or manipulate data. Whatever 3I Atlas reveals, the world will know, because hundreds of independent observers with their own telescopes and cameras will document it and share their findings immediately. This openness represents both the best of modern citizen science and a check against the kind of secrecy that fuels conspiracy theories. There will be no cover-up, no hidden data, no secret knowledge held by government agencies while the public remains ignorant. Avi Loeb's question, "Who knows what will happen?" posed before perihelion, now has a timeline for answers. By late November, we'll know if the trajectory changed. By December, we'll have comprehensive spectroscopic data on the post-perihelion composition. By February 2026, JUICE data will arrive. By March 2026, Jupiter flyby observations will provide the last significant data point. The mystery that began on July 1, 2025, when Atlas in Chile first reported an unusual moving object, will be resolved not on a single dramatic day, but through the patient accumulation of evidence that defines how science actually works. December 19, 2025, stands as a symbolic endpoint, the closest approach when Earth gets its best view, but the real answers will emerge gradually from the combined weight of hundreds of observations, dozens of telescopes, multiple spacecraft, and the collaborative effort of an international scientific community determined to understand what this object truly is. Whether we're witnessing the oldest comet ever observed or the greatest discovery in human history, we'll know for certain before 3I Atlas fades from view and begins its eternal journey back into the cosmic dark from which it emerged.